I am screen sharing. I don't know what that means.
Disabled. Is that why half of my face is cut off? No, I'm kidding.
All right, well, let me make sure there's no one in the waiting room.
Matthew, what is an atom?
What is?
And what is a polynomial?
Glad you asked that.
Yeah, it's going to be so relevant. All right, let's do this thing. So yeah, we've been going back to basics. You know, I appreciate you guys sticking with this. You know, we're, in theory, talking about quantum mechanics, but we spent the last time talking a lot about pebbles and integers, rational numbers, complex numbers. You know, whither is it tending? We shall see. Today, hopefully we'll get through these next two sections, we'll see. So last time we left it at the complex numbers, and we were very excited because they turned out to be basically the algebraic closure of the elementary operations of arithmetic. Add, subtract, multiply, divide them, exponentiate them, take roots. And we developed, you know, an interpretation of them. We thought about, you know, the hypotenuse of the triangle being a real number, about imaginary numbers being points on the complex plane. Now that, you know, following our sort of analogical logic, the next step, we should take complex numbers to be kind of like atoms that we can join together into a composite. And that is a polynomial. So here we will have a lightning review of interesting facts about polynomials. So, you know, a polynomial is a function, and it's defined quite like a base n number, but where before what was like the base is now a variable. And we're allowing these to be generally complex coefficients, and we can plug in complex numbers into our polynomial. And you see, you know, we got some powers of z weighted by the coefficients. We all know this. Two famous things you can do with polynomials that will, you know, end up bearing a lot of fruit is differentiate and integrate them. We can, oh, there's a little typo here, it should be dx. You know, the derivative of x squared is 2x, and inversely, the integral of 2x is x squared plus a constant. We could have polynomials with a finite number of terms. We could even have polynomials with an infinite number of terms. So for example, sine and cosine. We can define the derivative of a function as the change with regard to x, if that's the input. And you know, we all know for a real valued function, you can imagine this like the slope of the line tangent to the curve at that point. You can imagine choosing 2 points on the curve, bringing them infinitesimally close together, and you're gonna get a linear approximation to the curve at that point. Inversely, integration is like summing the area under a curve with little rectangles and imagining shrinking the size of the rectangles to be infinitesimally small. Okay, but then you look at a picture of sine and cosine graphed out, and just through visual inspection, you can see that the derivative of sine is cosine, and the derivative of cosine is negative sine. You know, whenever sine's at its peak, its tangent line's a horizontal line, and behold, cosine is 0 there. When cosine has a peak, sine is 0. And it's the whole way through. And there's this fourfold pattern. You take the derivative of sine, you get cosine. Derivative of cosine, you get negative sine. Take the derivative of negative sine, get negative cosine. Then take the derivative of negative cosine, you get sine. And so we go full circle. So whereas a finite dimensional polynomial will eventually give you 0 if you differentiate it enough times, an infinite dimensional polynomial can be differentiated an infinite number of times. One essential thing to know is about, you know, a Taylor series. You could take an infinitely differentiable function and express it as a Taylor series. Powers of the variable weighted by the nth derivative. So this term here is, you know, the second derivative. got a little factorial underneath, and dealing with the, second power of x. So
So,
then,
Matthew, does this prove determinism?
yeah, I mean, if,
Or is that next
you really
week's
have it's
lecture?
pretty amazing to have an infinite number of derivatives. I mean, that's powerful, that's potent stuff. It's really true.
But this proves determinism, mathematically.
Well, certainly of the description. So, at this stage, we can talk about Euler's famous identity. I alluded to it in the previous section about complex numbers, where we can represent a complex number as some r to the ei theta. So we can see how that works here. This is classic, beautiful proof. You can get the Taylor expansion for sine and cosine just from the formula above, where we can take the derivatives. And they form these nice little series here. Oh yeah, and I should also mention that these are transcendental functions, and part of what that means is that insofar as they have to be represented as infinite dimensional polynomials, they can only be sort of defined with an infinite amount of algebra. We can do the same thing, expand the e to the x as a Taylor polynomial, and we get this little series. Very nice looking. And if we plug in e to the ix, we can rearrange things so that we actually have the infinite series for cosine over here as the real part, and the infinite series for sine as the imaginary part. So we've proved that e to the ix equals cosine of x plus I sine of x. And the intuition is that as you wind around the unit circle, the x-coordinate traces out a cosine, and the y-coordinate traces out a sine. Okay, we're going to come back to all this, obviously. But let's consider finite dimensional polynomials. Classic thing you can do, solve for the roots. You want to find the zeros of this function. Because there's this amazing fact, which, when you learn about it in high school or whatever, I'm not sure if it seems obvious or non-obvious, but it actually is pretty amazing. So the degree of a polynomial is the highest power of the variable that appears within it. And it turns out that a degree n polynomial has exactly n complex roots. So we can take a polynomial like this, which is like a sum in powers of z, and express it as a product of these roots, z minus a root, z minus root, z minus root. The only catch is that these roots are left invariant if you multiply the whole polynomial by a complex number. So the roots define the polynomial up to multiplication by a complex scale. And so we can think of this kind of by analogy with, the prime numbers, just like a composite, whole number contains within it like an unordered collection of primes all multiplied together. We can think about polynomial as an unordered collection of complex numbers juxtaposed.
I feel that you often are speaking allegorically.
Well,
and so you have an intention. Like, for instance, you went on in your first talk, and what you were really talking about was quantum computing, as you were looking at the issue of black holes. So I feel that there is an allegory here. Do you want to tip us off a little bit to why there is this slow build, this slow preparation, because you are doing, where are you taking us?
Yeah, so I mean, one thing that I always struggle with is how to find narrative in math, because once you immerse yourself in the world of mathematics, everything is kind of connected to everything else, which is kind of like why it's cool. But one of the things that presents a problem, because like, how do you say it? How do you tell a story? And so, the kind of the frame I've been using is that, I kind of do believe this, that in some sense, the mathematical structures we use are kind of like fractals. Like, I don't mean it like literally, like a fractal, like a particular map, but that the mathematical structures we use are like the same logical patterns seen, at greater and greater scales, greater sophistication, the same kinds of, analogies being worked over again and again and again. In the case of, we're going to see today that we can describe a quantum spin state as a polynomial where the roots are quite relevant. We can even get equations that govern the motion of the roots and reconstruct the quantum dynamics like entirely from the roots. So that's sort of where we're going. And, we will also see, yet more analogies as we go on. But yeah, no, it's a great question. Yes, this has been like a very slow burn, and I have an ulterior motive. It's very true. So it's worth spending a moment talking about the fundamental theorem of algebra, because it's a cool proof. It's like, it's not even that difficult if you've ever seen this. First thing to remember is that if you have a complex number z to the r to the ei theta, and if you raise it to a power, you just get r to the n times e to the I n theta. All right, so suppose you have a polynomial, and you imagine that z, the input, is like very large. For very large z, the difference between the z to the n minus 1 and the z to the n term is quite considerable. And we can say that the polynomial is dominated by its largest term. Now imagine tracing out a big circle in the complex plane corresponding to different values of z. Call it the input plane. So we're going to go in a big circle in the input plane. If we look at what f of z is doing, it's similarly winding around the circle, but n times as fast because of this little fact over here. With, a little wiggling around the circle corresponding to the other terms, but we've treated those terms as essentially very, very tiny. Now we imagine shrinking that big circle in the input plane down to 0. But at 0, the function is just equal to its constant term, c0. So as the input circle shrinks down to 0, the output circle shrinks down to the constant term. To get there, the shrinking circle in the output plane must have passed the origin at some point, and therefore the polynomial has at least one root. You factor out that root, leading to a polynomial of 1 less degree, repeat the argument until there's no more roots left, and therefore degree n polynomial has exactly n roots in the complex numbers. And there's a nice number file video where a guy goes through that in a nice way. You don't even have to use any algebra to prove the fundamental theory of algebra. Really, it's sort of a geometrical / topological argument. There's other arguments, but that is by far the most intuitive. And this is true for if you're working over the complex numbers. So if you're interested only in real roots, it's not going to work. Sometimes it won't have roots. Looking ahead, this is going to be very important. Let's think about Vietta's formulas, which are very easy to derive. They just, if you imagine taking this polynomial represented in terms of the roots and multiplying it all out, you can get an expression for each coefficient of the polynomial in terms of the roots. And ultimately what you get is that, if you can, divide out by Cn, which is the largest term, and you get this, so that, the coefficient for the z to the Cn minus 1 term is just the roots taken 1 at a time and summed with a negative sign. And then the next one is the roots taken 2 at a time, summed. Roots taken 3 at a time and summed until finally get to the roots taken all at a time. And there's this little factor of -1 that you have to worry about, and so on. you can see, therefore, that the relationship between the coefficients and the roots is quote unquote holistic, just like the relationship between a composite whole number and its prime factors. Each of the coefficients depends on all the roots. And through this trick of taking this like unordered constellation of roots, 0 at a time, 1 at a time, 2 at a time, 3 at a time, we convert something that's unordered into something that's ordered.
Matthew, can I ask a question?
Mm-hmm.
Using this procedure, Vieta's theorem or whatever,
Mm-hmm.
has this facilitated factoring numbers into primes?
No, I mean, so what you're doing here is you're assuming you know the roots and you're working backwards to get the coefficients, which is relatively easy. It's another thing altogether to start from the coefficients and determine the roots. I mean, that's what we all spent hours and hours doing in high school or whatever, like solving polynomials, which is like not necessarily easy.
Shor's theorem has nothing to do with this then.
Not directly,
Yeah.
but similarly, you know, there's this asymmetry, right? It's like easy to multiply a bunch of primes together to get a whole number, but it's a little less trivial to, you know, figure out what are the primes within a whole number. If you did want to actually, you know, find the roots of a polynomial, you didn't know what they were, you know, and a little historical note, you know, in Renaissance Italy, mathematicians were cool, and there would be these huge public contests where people would solve, you know, equations in full view of the public. There were rivalries and people, you know, spying on each other, see if they had secret techniques for solving different kinds of, you know, equations. And it was in this environment that complex numbers were first discovered. If you wanted to cheat, you could just approximate the roots. And we'll see, actually, it's not really cheating because sometimes this is what you absolutely must do. One of the easiest ways, kind of similar to the algorithm that we used to calculate the approximation of square root of 2 last time, is just to choose a guess and then take the derivative. We'll take the function evaluated at the guess over the derivative evaluated at the guess and subtract it from the guess, and that gives you your new guess.
Lenore Evelyn Lewis.
And so you can see just from this image that this little technique is just going to get you closer and closer to the 0. And of course, this is like in the real case.
Okay.
On the other hand, we're familiar with the quadratic equation, where the root equals negative b plus or minus b squared minus 4ac over 2a, you know. And so this is kind of interesting, right? We can plug in the coefficients ABC, and we just fiddle around, and we compute the roots directly.
You need a square root in there.
Oh, you're right, yeah, square root. Yeah, I should just do that. Good eye. So yeah, is there always such an equation? Well, yeah, there is for, you know, degree 2, 3, and 4, but in general for polynomials of degree 5 or higher, there is no such closed expression that delivers the roots directly from the coefficients, and this is a famous result of Galois theory developed in the early 19th century. And in order to prove this theorem, Galois had to invent the idea of a symmetry group. And this will come to be very important. So, you know, you can think about symmetry group as a set of actions that you can do to an object that leave it invariant. And so you can kind of define the object in terms of all the things you can do to it that leave it the same. All the things that can be done, that can be undone. These different actions you can do are called elements of the symmetry group. And the rules are if you multiply 2 elements of the symmetry group, you get another element of the symmetry group. There's always an identity element such that when you do it, it does nothing. And every element has an inverse. So that doing the thing and then undoing the thing is like doing nothing at all. And there's also associativity, whatever.
Is that an allegory of how a spin 1/2 fermion maintains its half integer spin, even if it moves from an spin up to a spin down? Was that the allegory of symmetry there?
Well, we'll see that what I'm about to talk about is like, there's going to be finite symmetry groups and infinite symmetry groups. And when it comes to spin, we'll be considering the SU2, which is the double cover of the group of 3D rotations. And they form a group. And we'll see how we can represent that group with matrices. But
Matthew, was Galois on the way to discovering what we now call Lie groups? But he was killed in a duel, I believe, at the age of 20 or 21.
yeah, very famously, yeah. I mean, he was, it was the 1820s, I guess, 1830s.
Yeah.
France was, I guess, in its a certain reactionary phase. He was somewhat of a revolutionary. I mean, his father was like a local politician. Galois said something nasty about the king one time at a dinner party. There was a duel. Yeah, famous letter that he wrote. His last night in jail before the duel, he's like scribbling all of his Galois theory on this like one piece of paper. And
so this is all precursor to Lie groups, essentially.
so the groups that Galois considers are finite symmetry groups.
Oh. Okay.
And Lie groups are the continuous ones, and we will come to that. But yeah, so I mean, when Sophus Lie developed his theory, the idea was to like extend, what Galois had come up with to consider the symmetries of differential equations as opposed to just polynomials.
Is it the case that Galois is the idea of paying attention to the operations on functions and seeing their properties as a new insight into the functions? Like that was an innovative thought that was his.
Yes, and I mean, it wasn't his alone. I mean, his work sort of didn't become like super well known for a couple decades afterwards, and people like Abel and from which we get the name Abelian group, and others did a lot as well.
But sort of simultaneous with the groups and their interesting properties is this new take on a different way of looking, kind of like a dual way, a complementary way of looking at it. It
came out of this theory, like in answering the question of like, when is a polynomial solvable? And because like you could have come up with like the idea of a group, at any point really, but like in the history of mathematics, basically entered through this this route, studying polynomials. So we've already seen some groups, like the integers form a symmetry group where the action is addition. See, look, right? We could just add two numbers, get another number. 0 is the identity element. Negative A is the inverse of A. We've already seen that the rationals form a symmetry group where the action is multiplication, where the identity is, multiplied by 1, and the inverse is the reciprocal. Both of these groups, have a countably infinite number of elements, but there's, the classic one is like a group form from the permutations of the set. This is like the group of discrete symmetries of an equilateral triangle. You can do nothing. You can turn it 1/3 of the way, turn it 2/3 of the way, flip it across the axis, where A is the midpoint, flip it across B, flip it across C. And these correspond to the permutations of A, B, and C, the vertices. And like we've been saying, you can also have continuous symmetry groups where there's like an uncountable number of elements, where between any two group elements, there's a third element, like the group of rotations of a sphere. These are called Lie groups. Now it's worth noting that there's like a kind of atomic principle at work with regard to groups. Groups can be decomposed into subgroups, and you can decompose the subgroups into subgroups so you can't anymore. And what you're left with are the simple groups. So like, for example, the triangle group above has a subgroup, which is the cyclic group of 3 elements. The cyclic group is a group where every element is a power of some other element. These are just the rotations. You could represent these using complex numbers, where the group action is to like multiply by that complex number. And as points on the plane, these corresponds to, you know, vertices of an n-gon. Symmetry groups have been classified both at finite and infinite cases. And
Matthew,
Mhm.
does what you just say, is what you just said about multiplying by e to the I theta, isn't that restricted to groups whose elements are numbers? How could you, I mean, there are groups
Yeah,
whose
so these,
elements are not numbers, and it's not clear how you multiply by a number, some of these groups.
in this case, think about it like these act on complex numbers, but when you multiply these elements among themselves, they stay within this set.
Also,
So,
the rotation group, Andre, the rotation group is a continuous group, and you can multiply by you know, e to some imaginary power to just as a continued rotation.
like in this case, we're just considering the only thing we're allowed to do is multiply by these three numbers, and we can only multiply those three numbers by those three numbers. That's what forms the group in this case. Symmetry groups have been classified both in the infinite and finite dimensional cases, you know, up to some, whatever, some footnotes. So, you know, for example, the finite simple groups, there's famous classification of them, which took the better part of the 20th century to complete. And it was revealed that there's, you know, these different categories. The cyclic groups, 5 numbers of elements, alternating groups with at least 5 elements, groups that are finite but kind of resemble continuously groups, and then famously the 26 sporadic groups, the largest of which is the so-called monster group, which we're not going to talk about now, but you should definitely go read about it if you've never heard of it. There's a great video. Numberphile, again, has a great video where they talk to John Conway, RIP, who did a lot of work with monster group. Okay, so Galois' insight was to describe a polynomial in terms of the finite symmetry groups, group of.
I believe, just for interest, he said in that if there's one question he would like to have answered before he dies, and he can only choose one question to have answered, it would be, why does the monster group exist? So, and he's a pretty prominent guy, so that says a lot about the monster group.
Yeah, and there's interesting connections to physics as well, which are above my pay grade, but.
Yeah, it makes you want to ask the question of, if so much energy and thought has been put into this group, what about the next largest group?
Well,
I gotta feel bad for that
What
group.
have people thought about that?
Yeah, it's called the baby monster group. The next largest. It's the baby monster. And yeah, there's just all this cool stuff where you can kind of relate the other sporadic groups to the monster and the baby monster. There's like a whole elaborate story there that's very interesting. So like, how do you actually do this? We're not going to go into the whole thing of Galois theory, but just to give a feel, you know, what you do is, okay, you list out all closed algebraic relationships between the roots. So like A, B, and C were roots, you could have like AB equals 1 or A plus a half C equals 0 or something. And you're only allowed to use rational coefficients in the expressions. Then you look at all the ways that you can swap roots in those expressions that keeps them true, leaves them as true equations. Perhaps it's also true that A plus 1/2 B equals 0 and AC equals 1, in which case we could swap B and C in all these equations and they will still be true. If we list out all the possible swaps, all the possible permutations of the roots that leave these algebraic expressions true, they will form a group, the Galois group of the polynomial. And Galois' theorem is that when the Galois group of a polynomial can be decomposed into cyclic groups, it's precisely then that the polynomial is solvable. In other words, there's an equivalent of a quadratic formula, an expression involving integers and the basic operations of arithmetic. You plug in the coefficients, do a finite amount of algebra, and pop out the roots. If not, though, you got to approximate the roots of the polynomial, implying that the transformation from the coefficients to the roots involves an infinite amount of algebra. And this is generally the case for polynomials of degree 5 or higher, because for polynomials of degree 5 or higher, you can have, for example, the alternating group as a subgroup. Okay. Now we're going to talk a little bit about an infinite symmetry group. And here's how we're going to get there. So with polynomials, we can, evaluate them, integrate them, differentiate them, solve them. That's what we know so far. Evaluation is itself just a generalization of arithmetic. Think of a polynomial like a little bundle of some arbitrary amount of algebra under the heading of a single symbol. We could interpret 2 in these different ways, these different functions, right? Do we mean add by 2, multiply by 2, raise to the power of 2? But you might ask, if polynomials are supposed to be the new numbers, can we do arithmetic with polynomials themselves? And you're like, yeah, we can add and subtract polynomials. That makes sense. We can multiply polynomials, which is just combining their roots. But when we come to divide polynomials, there's an interesting development. If we have some p over q, or p and q are polynomials, it's possible that some of their roots will cancel out. But beyond that, where q has roots, p over q has poles. It goes to infinity there. But let us not fear to tread there. We just simply say, well, that's fine. And we invent the idea of a rational function, just like a rational number, except instead of a ratio between whole numbers, it's a ratio between 2 polynomials. And it's completely specified by its roots and poles. One consequence of this is that we can view rational functions as functions from the sphere to the sphere. If we plug in a complex number z into a rational function, we get out either a complex number or infinity. And so we interpret this in terms of the Riemann sphere. Complex number z via the stereographic projection, which we all know and love by now, gets mapped to an xyz point on the sphere. And the rational function maps this point to another point on the sphere, where infinity just corresponds to the pole projection, for example, the south pole. The simplest rational functions are known as the Mobius transformations. We've seen them before. You can see here, it says f of z equals az plus b over cz plus d. You got a root upstairs and you got a pole downstairs. And there's a restriction that ad minus bc does not equal 0. We'll come back to that. You can see just from the expression that if you plug in negative b over a into this, it's going to be 0. And if you plug negative dc into that, it's going to be infinity. Moreover, if you plug infinity in for z, if you take the limit as z goes to infinity of this, the b and the d become irrelevant, and you just get a over c. And if c is 0, then infinity gets mapped to infinity. Okay. Mobius transformations turn out to be one-to-one transformations. In other words, they map each point on the sphere to a unique point on the sphere. And these transformations happen to be conformal. In other words, they preserve angles, but not distances. And they take circles to circles. Another way of saying it is, if you figure out where 3 unique points are mapped to, you can figure out where all the points are mapped to. Geometrically, you can imagine that we have a set of points on the plane, map them to the sphere via the stereographic projection. The sphere is just a unit sphere at the origin. Then we're allowed to rotate this sphere and translate it in 3 dimensions, and then project those points back to the plane. In that way, all Mobius transformations can be obtained.
Matthew, isn't this almost clear from just look at the definition of the function? Obviously, if you multiplied a, b, c, and d by the same number, it wouldn't change anything. So there's really only 3 degrees of freedom there. So if you know 3 points, you know everything.
Yeah, nice. Yeah, sure. That makes sense to me. The Mobius transformations consist of combinations of rotations and boosts of the sphere, and also flipping the projection axis, in the sense that you have this plane, we're allowed to rotate the sphere in 3D, so we could rotate it like under the plane, which would be like flipping the projection axis. There are in essence 6 basic rotations and boosts, 3 rotations and 3 boosts in X, Y, Z directions. And this relates to those 6 degrees of freedom in the geometrical picture. And we'll come back to the fact that this number 6 later on. So for example, we can rotate the sphere 180 degrees around the x-axis with 1 over z. Obviously, this should fix the points 1 and -1 because those are the points on the x-axis. And indeed, that's true. If we rotate a half turn around the x-axis, we should flip y plus and y minus, and the same for z. So the Mobius transformations actually form a group, a continuous symmetry group. So like, for example, we can check the group composition law. If we have f and z, we could imagine the composition, f and g, we could imagine the composition of f and g, where we just, evaluate g and then plug that in to f. And if you work out the algebra, that itself has the form of a Mobius transformation. And indeed, we know that we can rotate our sphere around one axis, rotate a sphere around another axis, and then there's a third rotation that can take us there directly. If we consider higher order rational functions, like with more roots and poles, they won't be one-to-one. In fact, they won't be linear. This is obvious since all the poles get mapped to the same point, infinity. And if you have multiple points mapped to infinity, then it can't be one-to-one. But a rational function is defined by its roots and poles, so that we could imagine Mobius transforming those roots and poles, which takes them each to another set of roots and poles uniquely. Since a Mobius transformation maps each point on the sphere to a unique point on the sphere, it follows that a Mobius transformation maps each unique rational function to a unique rational function. And so the Mobius transformations, which are just the simplest rational functions, actually form the automorphism group of the rational functions. In other words, the group of transformations of the rational functions to themselves that take each rational function to a unique rational function.
Matt, can I ask a question? This also relates to, obviously, to special relativity. Was this work done? Did Mobius precede Lorentz and Fitzgerald and Einstein?
Yeah, he was more of a 19th century guy.
So he essentially determined special relativity, at least mathematically. And yet Lorentz and Fitzgerald are given credit for, it's called the Lorentz-Fitzgerald transformation.
I don't think Mobius suspected the physical interpretation of it in terms
Well,
of...
neither did Lorentz and Fitzgerald. They thought it was math. It took Einstein to say, hey, wait a minute, this is reality.
Yeah.
But so this is mid 19th century?
Yeah, mid 19th century.
So the bottom line is that all of these guys were stealing from each other.
Yeah, well, it's like, I mean, this often happens, right? Mathematicians will just like investigate something because it's cool, and then the physicists will realize like it's important.
But even the terminology that you're using, or is this modern terminology, a boost?
Yeah, he didn't use the term boost.
He didn't use that term because that's special relativity. Yeah, okay.
It was like in the 50s, and I would say it was like Penrose who like really emphasized this this way of thinking about it. I would say I think he made it a little bit more popular.
Matthew, can you back up a little and just say that thing about how Mobius transforms functions? Is it that z becomes a function in his equation, that you take a polynomial and replace z by that polynomial?
Here? Right, so the input z represents a point on the sphere. So we're interpreting that.
Yeah, I got that part, but then you said the next part, you said a similar kind of thing.
Yeah, so like what we're doing here is we're just taking g of z and plugging it in for z in the expression for f.
So when you do this then you said something about generalized polynomials.
I'm sorry.
Say again what you said about Mobius transformations being somehow fundamental for generalized polynomials.
So if you have a rational function, like in general, it's just a polynomial upstairs and a polynomial downstairs. And so that the one upstairs in the numerator can be factored into roots. The one at the bottom can be factored into roots. Now, you could just imagine Mobius transforming all of those roots and poles. That's going to take...
Wait. So you're taking something with many, you're taking a rational polynomial that has many powers and just putting it into Z here, which is only a first order polynomial. You're taking an nth order polynomial and replacing it an nth order rational polynomial and putting it in to a first order rational polynomial.
Or maybe the other way around, like taking the higher order rational function and then plugging in the Mobius transformation into it. I think it works. There might be a subtlety there. I just thought the easiest way of thinking about it was to just take the roots themselves, the roots and the poles, like literally those complex numbers, and Mobius transforming them, because that's going to take a constellation uniquely to another constellation.
So then Z becomes, so Z is one of the roots of the
variable itself instead.
So Z is one of the roots of the n degree polynomial. Is that what you're saying? Taking Z and putting it into the Mobius function, where Z is a root of an n-dimensional polynomial?
Well, Z is just the variable. Like, you know what I mean? Like if you look in this one, the root upstairs, would be, negative B over A. Like if you plug that in for Z, it's going to go to 0.
Okay, so say again what you said about Mobius function being somehow a basis for this.
It's like, yeah, I mean, the simplest way I've been thinking about it is like, if the rational function has a set of roots and a set of poles, and now we have this thing, a Mobius transformation, which takes the roots and poles uniquely to another set of roots and poles, we get another rational function. And if you imagine
wait, this is what we said before. So what you're doing is you're plugging a root or a pole into Z in that.
Oh, I see what you're saying. Yes. Totally, yeah, I'm sorry. I was saying, like, that's the way I was thinking about it. I think you can also do the other thing, which would be like, take the rational function of like whatever order and plug in a Mobius transformation of Z into the variable instead of transforming the roots. I didn't go through the algebra of that, but up to a factor, that should be the same thing. So, okay. So we know that, with the Mobius transformations, there's this connection to special relativity, where we can interpret boosts in terms of, one's velocity. And, we'll come back to that. So we have a new kind of number, a rational function, which is a ratio of polynomials. We can apply algebra to them just like normal numbers, even as they themselves represent bundles of algebra. They can be defined by a set of poles and roots, which are like the primes, the atoms of a rational function. We can think about a composite as a constellation on the sphere, a set of x, y, z points. And there's some new operations, integration, differentiation, and solving, and a new understanding of atom in terms of symmetry groups and their subgroups. Yeah. That's that part. That was like a little lightning review of polynomials. Okay, now we're gonna
Wait. I'm sorry.
Oh, no.
I'm sorry if I'm so slow on this. So how did we get from the roots to the sphere again?
Sorry, I went over that quickly because we talked about it previously, but you use the stereographic projection.
Okay.
This shows it usually I have it where like the plane is cutting the middle of the sphere, but yeah, you know, something like that. Okay. This part, you know, yeah, it's keep asking questions. You know, this, you know, when you're talking about this stuff, it's like one always wrestles with the question of how self-contained to be. So I ended up, you know, putting in a lot of somewhat, you know, basic things. Like if you've taken a linear algebra course or something, a lot of this will be familiar. So, you know, parts of it, I'll you know, I won't dwell too much on, but please, like if, you know, there's a question, just ask. So, all right, now we're here. You know, if before we gathered complex numbers into polynomials, well, you know, naturally we have to gather up polynomials to form some kind of higher order composite, which should provide perspective for polynomials, and which can be viewed as a yet higher order generalization of a number. And the concept that we're looking for is precisely that of a matrix, AKA a linear transformation, AKA what's called an operator, often in quantum physics, even an observable. And we'll find hiding within the whole theory of differential equations. And we've already seen matrices and vectors implicitly in a lot of what we've been talking about. Whenever we work with, you know, XY or XYZ coordinates, we're implicitly using the idea of a vector space. Integration and differentiation turn out to be linear operators. Mobius transformations can be represented as 2x2 complex matrices with unit determinant. And in general, matrices can furnish representations of symmetry groups, able to do justice to the law of group multiplication, which is not necessarily commutative, so that A times B does not equal B times A. And we know this, you know, intuitively, like the order in which you do rotations of the sphere matters. You do this first, and you do this, versus you do this first.
Matthew,
then
I'm sorry.
Point.
You just again went too fast for me.
Okay.
If you're saying that, I want to contrast two things, and you tell me which one you're thinking.
Okay.
Either a matrix multiplying a vector where the vector elements are complex numbers versus a matrix multiplying a vector where the vector is a complex number. It's one of its elements being the real and one being the complex. Which is the way you're thinking right now?
The former, although we will be discussing the latter shortly. Yeah, totally. That's a great question. That's going to come up. We're going to talk about different ways of interpreting the complex inner product in a moment, and we're going to get exactly that issue.
Was that Andre Mirabelli? Is that who that was? You're so Socratic.
It's great, you know. Plato wrote in dialogues for a reason. You know? So a vector space it consists of multi-dimensional quote unquote arrows called vectors and scalars, which are just normal numbers. You can multiply vectors by scalars, add vectors together. You always get a vector in the vector space. You could have infinite number of dimensions, so you could have finite or an infinite number of dimensions. And it turns out that polynomials form a vector space. You can think about the monomials, the powers of Z, as being the basis vectors. When we've worked with real vector spaces, you know, anytime we've used XY or XYZ coordinates, you know, for polynomials, we're going to be working with complex vector spaces where we allow our polynomials to have complex coordinates. And in either case, we can expand a vector in some basis, in some reference frame, some the chosen directions that we're going to use to describe our vector. A vector as a list of components is basically meaningless without reference to which direction each component refers to. And, you know, for 3D real vectors, you know, everyone just uses the standard basis, 1, 0, 0, 0, 1, 0, 0, 0, 1. Any 3D point can be written as a linear combination of those three vectors. They're orthonormal, they're at right angles, and of unit length. But, you know, any set of linearly independent vectors can form a basis. We'll generally be sticking to orthonormal vectors, but we'll see an interesting example of the other kind. linear independence just means that each vector cannot be written as a linear combination of the other vectors, where linear combination means a bunch of vectors, each multiplied by some scalar, added up. And you can see that the powers in a variable act like basis vectors in the sense that, like, if you add two polynomials, you know, the coefficient of the z squared term gets added to the coefficient of the other z squared term, and the same for each power. You know, for real vector spaces, it's easy to define the length of a vector. It's just the Pythagorean theorem. It's often written as this little dot product. And the idea is, like, you just take a vector and square each of its components, add it up, and take the square root. Or you can think about this as this operation where you take a row vector and a column vector, multiply AC times BD, and that's the inner product. You could take the square root to get the length. This quantity will be 0 if the vectors are at right angles. One easy way to see this is that it can also be expressed, the length of u, times the dot product between u and v, or the inner product, is the length of u times the length of v times cosine theta, where the theta is the angle between them. And so from this one can, you know, flip it around and calculate the angle, the inverse cosine of u dot v over length of u times length of v. The inner product is crucial notion we will return to again and again. It gives us a way of defining lengths and angles. And there are many different inner products. Like, for example, in Minkowski space, the distance squared is given by, or the norm squared, I should say, is given by t squared minus x squared minus y squared minus z squared, where the component of time has a different sign than the space components. We could implement this as an inner product like this, where we stick this matrix in between the two vectors. And this matrix in the middle is known as a metric. And implicitly, you know, when we just multiply the row vector by the column vector, the metric is just the identity matrix. So we can expand a vector in a given basis by taking the inner product of the vector with each of the basis vectors. So here, the basis vectors are bi, and v is our vector of interest. We're taking an inner product. We'll come back to this notation, but, you know, it's classic quantum notation. And this will give you the components of the vector in the new basis. We could organize the basis vectors into the column of a matrix, so that applying the matrix to the vector leads to a representation of the vector in the new basis. We can see that matrix multiplication is a generalization of the inner product. It's the inner product of a column vector with, say, each of the rows in turn, or that of a row vector with each of the columns in turn of the matrix. You know, matrices have inverses. We can use the inverse transform. Well, they often have inverses. You can use the inverse transform to switch your reference frame back. Matrix times its inverse is the identity matrix. And multiplying matrices, not just multiplying a matrix by a vector, is just the inner product rule iterated again. The Mij component of a matrix or grid of numbers is the inner product of the ith row of A with the jth column of B. The multiplication rule for matrices is non-commutative and associative, and they have inverses often. There's an identity element. It makes sense, therefore, that we can represent symmetry groups using collections of matrices, encoding the group multiplication as matrix multiplication. And this is the basis of representation theory, and it's very important. Indeed, matrix multiplication might preserve some special property of the vector. For example, orthogonal real matrices, which have orthogonal unit vectors as rows and columns, have the property that the inverse is just the transpose. And they preserve the lengths of vectors they act upon. And so they form a group. Can represent rotations in any number of dimensions, real dimensions. For complex matrices, there's the unitary matrices, for example, such that their inverse is just their conjugate transpose. And they preserve the norm of vectors as well. Linear transformations allow us to represent shifts in perspective, like the most familiar way, you know, a scene seen from a rotated or translated point of view. So shifts in perspective can always be defined in terms of what they leave invariant, what they leave fixed. For example, consider rotations around the z-axis. They leave 2 points fixed, the North Pole and the South Pole. We're just rotating around that axis a certain angle. With that in mind, we can define the eigenvectors and eigenvalues of a matrix with this little equation, which says that if you have a linear operator or matrix M, then on an eigenvector of M, call it V, the act of matrix multiplication reduces down to just normal familiar scalar multiplication by M, which is the eigenvalue. In other words, M doesn't rotate the eigenvector at all. It just stretches or shrinks it, or in the complex case, complex rotates it by M. And a matrix can be defined in terms of its, with a footnote, can be defined in terms of its eigenvalues and eigenvectors, namely the special directions that it leaves fixed. Not all matrices have a complete set of eigenvectors, and sometimes there's different eigenvectors with the same eigenvalue, but an interesting fact is that Hermitian matrices, which play a crucial role in quantum mechanics, which are complex matrices that are equal to their own conjugate transpose, they all have real eigenvalues. And they have orthogonal vectors as eigenvectors. And so those eigenvectors form a complete basis or set of directions for the vector space.
Matt, can a Hermitian matrix have degenerate values, or do they all have to be unique?
They can have multiple eigenvalues that are the same.
So then some of the vectors would not be orthogonal. They would be the same vector, essentially.
No, you can have...
the eigenvalues would be the same, but the eigenvectors would be different.
Yeah.
Oh, okay.
Expressed in its own basis, which is, you could say, the basis formed by its eigenvectors, any matrix can be written as a diagonal matrix. And along the diagonal are the eigenvalues. An n by n defective matrix is one that has less than n linearly independent vectors. So we can't do that. We can't bring it to diagonal form, but it can be brought into block diagonal form, which is nice. And yeah, we won't talk about that too much right. Okay, here's a little argument. Just like a polynomial is composed of its complex roots, we can view matrices as being composed of polynomials. And just as polynomials kind of give context to their roots, a matrix gives context to polynomials. And in some sense, a matrix is a polynomial, but possibly distorted in perspective. And here's a nice way of seeing that. Consider how we find the eigenvectors of a matrix in just the simple 2 by 2 case. If we have a matrix A, B, C, D, we can look at our little eigenvector eigenvalue equation. A on an eigenvector should just equal lambda on that vector, where lambda is the eigenvalue. We rearrange things a little bit, and we reformulate this as saying that A minus lambda times the identity on the vector is 0. Therefore, since this matrix here, we want to give the 0 vector on V, it should not be invertible. Because obviously if a matrix sends a vector to the 0 vector, it's not invertible because you can't get anything back from the 0 vector. A matrix is not invertible when its determinant is 0. So we actually want this. The determinant is evaluated this guy times this guy minus this guy times this guy. So we, plug that in and we get this little polynomial. Lambda squared minus a plus d lambda plus ad minus bc equals 0. The eigenvalues are the roots of this polynomial, called the characteristic polynomial. We can express our matrix in another basis with the change of basis transformation. You just multiply from the left and right. We find that in a different basis, the matrix has exactly the same eigenvalues. In other words, the eigenvalues are left invariant under a basis transformation. The trace of a matrix is the sum of the eigenvalues, and the determinant is the product of the eigenvalues, and so they too are left the same. And so we can think about a matrix as secretly just being a polynomial, its characteristic polynomial, which defines some roots, which are the eigenvalues. But we use the matrix representation because it keeps track of the fact that we might be viewing the polynomial in a different basis.
Matthew, could you just go back and show that example in that two-dimensional?
Sure.
So you said that the trace is the sum of the eigenvalues?
Yeah.
So I see that the trace is A plus D minus 2 lambda. So how do you get that?
So when we're talking about the trace, we're referring to the trace of this matrix,
Oh,
A, B, C, D. Yeah.
okay.
That's because for a Hermitian matrix, you can always diagonalize it,
Precisely.
right? And so the trace is the sum of the eigenvalues.
Yeah, 100%. One interesting fact is that the matrix itself is a root of its characteristic polynomial, reinterpreted in terms of matrices. So like if the characteristic polynomial was az squared plus bz plus c, such that the eigenvalues were roots, then if you plugged in a for z and reinterpreted the powers of z in terms of matrix multiplication, then you'd get the zero matrix. So a times little a times the matrix squared plus little b times the matrix plus c times the identity is going to give you 0. So there you go. That's kind of cool. And looking ahead in quantum mechanics, two observables are quote unquote simultaneously measurable when the Hermitian matrices can be simultaneously diagonalized. One, perhaps the original use of matrices was to solve systems of linear equations. For example, if we had this system of linear equations, we could solve it as a matrix equation. You see, if you just follow out the matrix multiplication of this, you get ax plus by plus cz equals k, and so on and so forth. And so we can rewrite the system of linear equations as just this matrix multiplication, a, the matrix of the coefficients times x, the vector of the variables equals y, whatever you want them to be. And you luck out if A happens to be invertible, because then you can just invert the matrix, multiply y by the inverse, and then you get your solutions. Many interesting properties of matrices become evident when you consider the homogeneous case, when ax equals 0. If this equation is true, it means that x is in the null space of A, which is a vector space of its own. If you add two vectors in the null space together, you also get a vector in the null space because matrix multiplication is linear. So if you have big A on little a and b, and big A on little a and big A on b are both 0, then obviously, this is going to be 0 too. Okay, rank nullity theorem, we'll come back, skip that. So there's an intimate connection between this stuff to the theory of differential equations, which are problems where one's given an algebraic relationship between the derivatives of a function, and you're asked to find a set of equations that satisfy those relationships. For example, a wave equation, whether classical or quantum. And ultimately one sets up something like this. Some operator on phi equals 0. Even if one starts off with, that equals like something else, one almost always recasts things to get a quote unquote homogeneous problem where it equals 0. Since such solutions form a vector space, as I just said. And, an intuition is that, like, suppose you were solving a differential equation governing a vibrating one-dimensional string fixed at its ends. You could describe that in terms of, you know, XY coordinates over time about, you know, where the string is. To homogenize the problem is as much to consider the string in its equilibrium position, which doesn't change in time, as a reference frame, and to describe a string's behavior as deviations from that equilibrium.
So is that equation only for a string in its equilibrium position, or is it for a string in motion?
I mean this quite generally, yeah. This is just a simple example.
I mean, can h phi equals 0 be a string in motion, or is it only in its equilibrium position?
No, it can be in motion, yeah.
By the way, this is also known in cosmology. This is the Wheeler-DeWitt equation. This is the Hamiltonian for the entire universe. So what is that saying for the entire universe?
Yeah.
I mean, we don't necessarily believe that that's true, but I mean, what would be in the interpretation for the entire universe? Just that the Hamiltonian doesn't change, I guess.
Yeah, I mean, like we were talking about before, that, you know, such an equation, you know, when we think about quantum entanglement and everything, is as much to say that time is always measured with reference to clocks in the universe. So let's make a little more concrete this connection between matrices, linear transformations, and solving differential equations using a very simple example. So let's take H to be a differential operator, which means that's an expression involving like variables and this operator D. And D means take the derivative, okay? So for example, we could have a differential equation, simple single variable case, ordinary differential equation, y double prime plus y prime minus 2y equals 0. Couldn't imagine anything simpler, okay? We could rewrite that in terms of this differential operator D as d squared plus d minus 2 all times y. And you see when you multiply it out, d squared, you know, gives you y double prime. When it acts on y, d acting on y gives you y prime, and so forth. Now, let's consider this polynomial, d squared plus d minus 2. It has two roots at 1 and negative 2. And this equation is true if you plug in these eigenvalues d, and also if you plug in the big D. And so we can think about this as the characteristic polynomial of like some linear transformation. I should put a footnote here, but just check this out. Let's organize the eigenvalues into this matrix. We had 1 and negative 2, so we make this diagonal matrix. Now, if lambda is a root of the polynomial, then it turns out that e to the lambda x is a solution to the differential equation. And you can see this quite clearly. If you take e to the lambda x, I'll make this a little bigger, and you take its second derivative plus e to the lambda x first derivative minus 2 e to the lambda x, you get lambda squared e to the lambda x plus lambda e to the lambda x minus 2 e to the lambda x. And that's as much you can divide out by e to the lambda x, and that's just the polynomial we had before, lambda squared plus lambda minus 2. So if you have two roots and two equations, e to the x and e to the negative 2x, then a general solution is a linear combination of them. Y equals a e to the x plus b e to the negative 2x. The solution space forms a two-dimensional vector space, and you can freely choose a and b. And what you'll get when you sum them is always also a solution to the differential equation. So we could write this in a form that, you know, you're kind of like more familiar with in terms of quantum mechanics, maybe, you know, if you've seen stuff, as this. If you imagine y0 as like a little vector that's just the coefficients a and b, then e to the hx just gives us our general solution where or it gives you the particular solution, you know, that comes from specifying the a and b. You can see that this matrix that we had here, 1, 0, 0, negative 2, acts like taking the derivative of this vector. You see, when I multiply this matrix by this vector, e to the x gets multiplied by 1, and e to the negative 2x gets multiplied by negative 2. And so we see there's an intimate relationship between matrices, differential equations, and exponentials. Okay. A word on...
Now, Matt, is that only for linear differential equations?
Yeah.
Because an exponential in general is not a solution
Yeah.
to differential
We're
equations.
talking about, linear differential equations, okay, so now like a word about complex vector spaces. We're going to use the bracket notation where, we have a row vector being a bra, column vector being a ket, and the elements are complex conjugated. So the inner product for complex vectors, you take the vector, the other vector, complex conjugate it, and then, multiply them pairwise and sum. This inner product is going to be a complex number. But similarly, just as for real vectors, if the vectors are orthogonal, the inner product is 0. And we can use the inner product to expand a vector given a set of basis vectors. But, complex vector spaces are like a little weird. And so let's build like a little bit of intuition for how they work. I mean, the first thing to notice is that, when we add two complex vectors, the individual components can cancel out in like a whole circle's worth of directions, not just in terms of positive and negative like real vectors. And this is what ultimately leads to, quantum interference down the road. Let's just take an example. Like this isn't even technically like a vector space, but let's just do it anyway. What if we just tried to form a one-dimensional vector space of just a single complex number? Alpha equals x plus iy. The length of this vector is just the complex number times its conjugate with the square root, or square root of x squared plus y squared. And then we could just, follow out the inner product of it. You have some other b, so b conjugate times a is whatever we're calling the inner product. So let's actually like multiply it out. We'll write BR and BI for the real and imaginary parts of B, and AR and AI for the real and imaginary parts of A. We do a little algebra, and we get that the real part is just BRAR plus BIAI, and the imaginary part is BRAI minus BIAR. Now, let's define this guy, A with an arrow, to be just the vector ARAI. In other words, the two-dimensional real vector corresponding to the real and imaginary parts of the 1D complex vector. This is sort of getting at the question from before. Similarly, we can form a two-dimensional real vector from the real and imaginary parts of B. And so we can see that the real part of our inner product is just the normal inner product on the two-dimensional real vector space, so defined. If you take the inner product of this, it's just ARBR plus BIAI, and that's exactly what we have here. But, so that's sort of interesting. Okay, so it's like take a complex vector space, turn it into a real vector space of twice the dimensions. Then the real part of the complex inner product is just the normal inner product in that higher dimensional real vector space, okay? But what's the imaginary part? Up here, we see that it's BRAI minus BIAR. We could organize that into a determinant. where we stick the vector for B and the vector for A as the rows of this determinant. It happens that the determinant is the signed area of this parallelogram. So that if we have AB and A and CD, then we evaluate the determinant and we get this. So that's interesting. If we just have like a little complex number and we, upgrade it into a two-dimensional real vector, then the inner product of those two little arrows in 2D give us the real part, and the area of the parallelogram formed by those arrows gives the imaginary part. So if this is just, the one and this one's the other, then the inner product between, the lower part of this parallelogram, the bottom of the parallelogram and the left part of the parallelogram, the inner product between them is just the real part, and then the area of this parallelogram is just the imaginary part. And, when we work with, n-dimensional complex vectors, we're just adding up the components. So, you can imagine the real part is just the sum of all the real inner products, and the imaginary part is just the sum of all those areas of parallelograms for each component. But there's another way of thinking about it. So we're going to come back to this in like way later in terms of this connection to area when we talk about like a symplectic form. But let's not get there now. Another way of thinking about this is like, well, we could also describe this as just the inner product between BR, BI, and AI negative AR. And now here's a little thing that, one should know. If you take a 2D real vector and flip its components and negate one of them, that just rotates it 90 degrees. So like if you have the point 2, 3, and you take the point 2, negative 3, they're going to be at right angles. And so actually there's a weird way of, like, it's kind of a surprising thing.
You said that wrong. You said that wrong, but that's okay.
Did I say it wrong? Sorry. 3, 2, and 2, negative 3. So to get the imaginary part, like, instead of finding the area of the parallelogram, we could rotate A 90 degrees and take the inner product with B and get the same answer.
Well, I can always be interpreted as a 90-degree rotation because -1, which is I squared, is 180-degree rotation.
Sure.
So I is always a 90-degree rotation. That's what it is geometrically.
Well, but it gets even deeper here when we talk about these actual higher dimensional spaces. Because, like, for example, like, check this out, right? If we have two 2D vectors, say 1, 0, and 0, 1, if we form the complex inner product, we just get I. So even though that those vectors are like orthogonal in a real sense, they're not in a complex sense. The inner product is I. If you have two parallel 2D vectors, they're going to have a complex inner product of 1. And in this case, where we're just considering one complex number, the complex inner product can only be 0 if one of the vectors is the 0 vector, which is actually a proof that one complex number is not a complex vector space. Okay. But once you have an n-dimensional complex vector, it really is a complex vector space. And so what does it mean then for two vectors to be complex orthogonal to each other? It means that they are orthogonal to two orthogonal vectors. In other words, A is orthogonal to B and also to B rotated 90 degrees. In other words, that the one vector is like a line perpendicular to a plane. And so we see that there's something intrinsically three-dimensional about the complex inner product. if a 90-degree rotation in like high dimensional space seems abstract, just consider like if we had a 2D complex vector, we could turn it into a 4D real vector. And look, if we just swap the real and imaginary parts and negate, the real inner product will just give us 0. So that's
Matthew, just from my intuition, can you go back a little and say it a little slower? This fact about 2D vectors at right angles. Explain more clearly what that sentence means.
Yeah. So you have a point on a plane. That's a 2-dimensional real vector. And you could treat it as a real vector space of 2 dimensions. And you can define the inner product. We could also interpret each of those vectors as a single complex number. And we could try to find the complex inner product between 2 complex numbers. And it turns out that's ill-defined because it's never going to be 0. As you can see here, if we, just as an intuition.
What is that supposed to mean? It's supposed to be that you're thinking of it as 1, 0 is the real number 1 and the complex number 0?
Yeah,
Is that
exactly. Mm-hmm. The question is, you have a complex vector space and you're trying to interpret the complex inner product. It's useful to consider the 2n real dimensional space. And there, what the complex inner product means is that if you have 2 vectors A and B, to be complex orthogonal is for A to be at right angles to B, and also for A to be at right angles with B rotated 90 degrees.
So do the calculation of the complex inner product of those 2 vectors. What would it be? How would you, it would be, you'd be taking what?
Well, so if you had, A and B, or I did it up here, let's see. Here, so I just take a single complex number. I take the conjugate of B and I multiply it by A as a complex number. And I work out the algebra. And then here, you see this is just the real inner product on the 2n dimensional space. And the imaginary part is, you can think about this as this area of the parallelogram, or alternatively, as the inner product between B and A rotated 90 degrees.
Yeah, I see all that, but I still didn't get how you defined the inner product between complex numbers.
So,
I didn't get that.
Right, so technically speaking, to really get a complex vector space, you need more than one component. And I say that because for just a single complex number, the complex inner product can't be 0.
But Matt, you can always describe a complex number in its polar form.
Sure, you could do
And
that.
then you just multiply all the numbers in their polar form, and you can get the answer that way.
Right.
Very often, it's a lot easier. You'll get a magnitude and an angle.
Yeah, that tells you about multiplication, but I want to understand what inner product means in this.
Well, you would get the inner product if you multiplied them in polar form, wouldn't you?
Well, if you multiply the one by its conjugate, is what I'm saying. It's like the idea. And you can see that it'll never be 0 unless one of them is 0.
Yeah, because if you multiply something by its conjugate, you'll get a real number in polar form or in this form.
So let me say what I think you're saying. You're saying that if I look at a plane with points on it and I interpret them as real numbers, I take their inner product. But if I interpret them as complex numbers, what it means to take their inner product is just to take their product.
No, it means on the one hand to take their normal inner product, and then on the other hand to take the area of the parallelogram that they encode, or alternatively the inner product of the one with the other rotated 90 degrees. Like,
That's not what you said about, go back to where you pointed to me, that equation again. Just scroll back.
yeah, sure. Which one? Here?
Yes, right there. Look at that. All you're doing is taking the product of B star and A. That's
Yeah.
what you're doing. You're not taking an inner product at all. You're just taking the product of numbers.
Right. So the question was, you know, in a way, do like a single complex number, do they form a vector space? Do they form a complex vector space? Right. So like this would be, you know, if it was two-dimensional, obviously you just do the same thing, but there'd be two terms. And the reason that the complex numbers considered in themselves don't form a complex vector space is like what we're saying is that they can't be at right angles unless one of them is 0.
Is perhaps another way to get some insight? Although maybe it's clear based on that last comment. I was just thinking that like one might think that a complex number, it's got two parameters. A vector space, two-dimensional, it's got two parameters. Maybe it's the same thing, but a little further thinking is that, well, if you want it to be a complex two-dimensional vector space, then you actually need 3 numbers to have an arbitrary, let's say, reference. Like you can't just.
Yeah, you need 2 complex numbers or 4 real numbers.
Yeah, I mean, and you can always, like, if you want to define your first basis vector in the complex plane, in complex vector space, you could arbitrarily always choose, like, without loss of generality, choose one of the components to be real, you know, aligned to the real axis, and make it 1 even, and just by.
Okay.
Well, maybe you can't make it 1, but you can like have 1 just be real, but then the other component is some, you know, 2-parameter complex variable. Like whereas just one complex number, you got A and B, A plus IB. But like the simplest possible general vector in complex 2D space would be like one component is A plus BI, and the other one is like C.
Yeah, sure. Yes.
And so I think there's a 3-dimensionalness in the fact that you can only have it in 3. 3 is the limited, the smallest representation of the general.
Okay. Yeah, I'm down with that.
So if I'm thinking of what seems like another interpretation of your words, just follow along and tell me where I'm going wrong here.
Yeah.
If I have a plane where the axis is a complex number, so I have 2 complex axes, and I have a point on that plane, therefore a point is described by its complex first coordinate and its complex second coordinate. And now I take 2 points in that plane, or 2 vectors whose tail is at the origin, and take their complex and take their inner product. I would have the inner I would have the product of the first complex number with the product with the first coordinate of the second complex number, and then I'd have the similarly for the second, and so that's an interpretation of taking an inner product in of complex vectors, because in that case each component of the vector is a complex number, and that seems to have nothing to do with what you're talking about now.
Yeah. So yeah, like what I'm talking about is, you know, obviously a complex number has 2 parts. And so you could go in 1 of 2 directions. You could try to interpret that as a 1-dimensional complex vector space, or as a 2-dimensional real vector space. And, you know, in this case, you can kind of give a geometrical meaning to the complex inner product in terms of the real stuff. even though, as I keep emphasizing, it doesn't form a one-dimensional complex space. We're about to talk about two-dimensional complex vector spaces where, you can have vectors which are complex orthogonal. Like, it makes sense in the sense in that, like, if you're just working with a plane, and what it means to be complex orthogonal is for one vector to be orthogonal both to a vector and to that vector 90 degrees, that can only happen in at least 3 dimensions. Maybe, what I say will be a little more clear now that we talk about, an actual complex vector space. The simplest one, 2 dimensions. So
But Matt, again, is there any advantage to approaching it this way as opposed to just expressing complex numbers in their polar form, where you have a magnitude and an angle? So, and then you can just multiply all of them to get their, their dot product.
Yeah, totally. I only go into this in order to give a sense of the geometry, perhaps, involved in.
Right. Isn't there something to like that in a space not being defined until you have a defined inner product?
Yeah, sure. Mm-hmm.
So if you're struggling to come up with a complex inner product, then you don't have a well-defined space yet. So it's important to talk about.
I was just alluding to Victor's question before. Where is this leading?
Oh yeah.
For a moment there, Moishe was pacing back and forth, and I was wondering if you didn't arrive at spin soon, then Moishe was going to begin some intricate Tai Chi or capoeira routine, and we were going to be completely baffled. So yeah. So
speaking of spin, my head is spinning.
Bring us into the spin room. Only kidding.
It's about to.
Bernie for president.
More complex.
No, but where is this leading? Are you leading to spin? I mean, are we going to get a geometric picture of spin?
Exactly.
Yeah. Okay.
So before talked about taking a complex number or infinity and upgrading it to a little 2-dimensional vector. And the rule was we could take alpha, where that's a complex number or infinity, and form 1 alpha or 0, 1 if alpha equals 0. And we can go in reverse, take beta over alpha or infinity if alpha is 0. We went over this in one of the previous essays. So, what's cool about this is a complex projective representation. What it means is we can multiply this complex vector by any complex number, and it won't change the point that it represents on the sphere. We can think about this 2D complex vector as corresponding to various things. A direction in 3D with a length and a phase, thus representing like a classical spinning object, the direction being the axis of rotation, the length being the speed of rotation, and the phase being how far it's turned around the axis at a given moment. It also represents an incoming classical photon, which is specified by a 3D direction, certain color being its length, and a polarization or phase. Generally unnormalized 2D complex vectors are referred to as spinors. If we normalize the vector, so its length is 1, we can view it as the state of a qubit. For example, the spin angular momentum of a spin-half particle. And the rotation axis can only be inferred in that case, we're going to come back to this, as a statistical average. So that if we've quantized along the z-axis, then A times A conjugate is the probability of measuring the qubit to be up along the z direction, and B times B conjugate is the probability of measuring it to be down. And we're going to come back to that, but I just want to emphasize here that if you look at the normalization condition, A star plus B star equals 1, and we pull the same trick where we're like, let's just forget the complex part, so to speak, and realize that, each of these is, has 2 parts to it. We can describe this as, in terms of a 4-dimensional real vector space, where, say, alpha and beta are the components of A, and gamma and delta are the components of B. And if, alpha squared plus B squared equals 1 is a point on a circle, and alpha squared plus beta squared plus gamma squared is a point on a sphere, then this guy is a point on a 3-sphere. And so we can interpret our two-dimensional complex vectors as being points on a 3-sphere. And, you know, just like a sphere is a 2D space that loops around, you can think of a 3-sphere as a 3D space. If you go forever in one direction, you loop back around. And there's a whole interesting thing relating to this involving the Hopf vibrations, but you know, let's not dwell on that. Let's keep going. Okay, so let's get into the 3D geometry of the situation. All right, on the Riemann sphere, you have 6 cardinal points: 1, -1, I, -I, 0, and infinity. And those are x, the 2 x-axes, you know, 2 points on the x-axis, 2 points on the y, 2 points on the z. We can convert them into spinors using the little expression from before. So then we get these 6 little guys. One thing that's interesting about these is that these pairs of vectors, which represent antipodal points on the sphere, are complex orthogonal. So this is crucial. In this space, antipodal on the sphere means orthogonal in the complex space. Complex orthogonality is just saying that the 2 points are opposite to each other on the sphere. If you have a set of eigenvalues and eigenvectors, you can work backwards to find a matrix that has those eigenvalues and eigenvectors. So, like, let's do it in this following interesting case. Suppose—
So, Matt, excuse me. So what you said is, since you're saying the complex conjugates are antipodal, which means they're 180 degrees separated rather than 90?
Not the complex conjugates. Say 1 and 1 and 1 and -1. Those are complex orthogonal.
Complex
and when stereographically project to the sphere, they represent opposite points on the sphere. So yeah, it doesn't mean at right angles in that interpretation.
But what did you say? What was the conclusion? That they're—
So as if you think of these as—
they're complex orthogonal, but what does that mean? Complex orthogonal.
It means that their inner product is 0, or the complex conjugate of the one, you know, juxtaposed with the other one, or, you know, you take the complex conjugate and the guy and, you know, pairwise multiply and add them. What's your question?
No, so it's just that
This is not like complex orthogonal. It's a different kind of orthogonality. It's just the usual orthogonality in a complex,
like the one
complex
thing,
space.
The one thing to remember is, like, say, like, here, take this I case.
this is just how you're defining complex orthogonality.
Like, if I have one I got to take the conjugate of that if it's a row vector here.
Right.
And then I got one negative I over here. And then when I take the complex inner product between them, it's 0. So this represents the point at the y plus, that represents the point at y minus. And you can see that their x, y, z coordinates are just the negatives of each other. It's just 0, 1, 0, and 0, -1, 0. But interpreted as a complex vector space, those two vectors are at right angles.
So, and I guess you're leading to spin half. You're getting twice the rotation.
Yeah, so we can, that's exactly right. So look,
Yeah.
we derive from this the Pauli matrices, X, Y, and Z. These 6 matrices taken as pairs are the eigenvectors of the Paulis. In other words, these 2 vectors are the eigenstates of Pauli X, these 2 are the eigenstates of Pauli Y, these 2 are the eigenstates of Pauli Z, and the eigenvalues in each case are 1 and -1. So I like literally build it up. We imagine we have this diagonal matrix, which is, you know, 1 and -1 along the diagonal. Those are the eigenvalues. We can stick the eigenvectors as the column of this matrix here, take the inverse, and then doing C times the diagonal times C inverse gives you Pauli X. In other words, this is a vector with two eigenvectors. When it acts on the X plus point, it multiplies it by 1. And when it acts on the X minus point, it multiplies it by -1. And Y similarly, when it acts on Y plus, it multiplies it by 1. When it acts on Y minus, it multiplies it by -1. And so that's where the Pauli multipliers come from. One thing that's useful about them is that instead of going through all this rigmarole of like taking a complex vector, taking the ratio, stereographically projecting to the sphere, there's another much simpler, so to speak, of getting the XYZ coordinates. We just take the expectation value
You don't
of
even have to do that because
XYZ.
Michael has turned into XYZ. He is the coordinate.
Am I the only one who hears an echo?
No, I hear an echo as well, but
Yeah.
When
I
Matthew,
was enjoying my
we hear an
moment of
echo.
fame there.
Your doppelganger is talking about a half a second after you do.
It's a half a second instead of 15 minutes of fame. That's
Well, take what I can get. But yeah, there is an echo.
But only when Matthew talks,
Yeah.
not when the rest of us.
Oh, I think it was motion. I might mute you for a second.
I think I've heard that before. I think it's where he stands.
Yeah.
I think
Oh,
it's
I like standing too.
the
Right?
distance that you stand from us that creates the echo, I think.
Maybe if you just shoot your doppelganger, it'll clear up.
Okay, so we can now write our XYZ components as expectation values instead of going through this whole rigmarole involving the stereographic projection. We can
But actually, before you forget the rigmarole, I feel like I maybe looked away when there was this nice moment of seeing the organic origin of the Pauli matrices. So could you just repeat the view of this natural? It was the 4 points on the Riemann sphere. If you combine them in pairs, then they naturally, you're getting the columns of the Pauli matrices. Is that something like that?
Sort of, close, very close. So like, let's just consider the case of X. The numbers 1 and -1 as complex numbers, when they're projected to the sphere, are, this point and this point, X plus and X minus. We then convert them into 2D complex vectors, and we get 1, 1, and 1, -1.
And then there was a projection, stereographic. How did you go from -1 and 1 to anything complex?
So yeah, there's no complex part to it, but here's the rule. So if you have so in this case, it's like plug in 1 for alpha, and then 1, 1, and then you plug in -1 for alpha, you get 1, -1. Those two vectors are orthogonal. You can see it right here. We can then imagine that they are the eigenvectors of some transformation. So we stick them as columns of this matrix C. We then take the inverse of this matrix C, and then we take this diagonal matrix with the eigenvalues we want, 1 and -1. We'll see why we want them in a second, but then what C times D times C to the -1 does is it basically takes you from the basis of the eigenvectors, where like the matrix is diagonal, to the standard basis. And the result of that is the Pauli X matrix. This matrix, when it acts on this vector 1, 1, multiplies it by 1. When it acts on this vector 1, -1, it multiplies it by -1. And the construction is analogous for Y and Z. Does that make sense?
Yeah. I guess there seems to, like, the payoff of all that whole buildup seems to sort of be here, right?
Yeah,
Because you're giving this, like you could have just derived Pauli matrices from other motivations, but this seems to be this very natural geometric origin. But
that's why I
but
like.
can you comment more on the sort of like how to be like, should I still be thinking of the Riemann sphere while I'm looking at the Pauli matrices, because those rotations using the the 1 minus 1 eigenvectors, I can just think of that in like a regular 2D space. I mean, I don't have to keep the notion of Riemann sphere in my mind for all but the part that you're explicitly talking about, the Riemann sphere part, but it seems like there is an important connection. So how do I continue to invoke in a meaningful way the Riemann sphere story? And
Yeah, well, so I mean, for example, like I'm saying, if you have just a qubit state and you take these expectation values, you get the XY coordinate of whatever you started with. So this is like another way of calculating that. And in terms of the physics, it's interesting that you can interpret the direction in which something is spinning as a quote unquote like expectation value. So like an expectation value is, one's expected winnings. You take all the different rewards and losses, you weight them by the probability of those outcomes, and you sum the result. We can rewrite, say, this expectation value like this, where what we're doing is we're getting the length squared of psi on each of the eigenvectors, and we're multiplying it by the eigenvalue. We interpret this as a probability that psi is in one of the eigenstates. That's like x plus or x minus or z plus or z minus. That gives a probability.
Can you back? I'm sorry.
Mm-hmm.
Can you back up to the Pauli matrices?
Oh yeah.
It seems that what you're doing is you're reverse diagonalizing them.
Yeah, exactly. Switching from the basis formed from the eigenvectors to the singular basis. Yeah.
So you're just rotating them from their diagonal form to the standard form that we're accustomed to seeing.
Precisely. Yeah. And you can see, you use this complex vector representation of.
And why are we? So why aren't the Pauli matrices the diagonalized versions? Why are they the ones we're accustomed to seeing?
Well, because they can't be all simultaneously diagonalized.
Oh, okay.
They don't commute.
Because of the exclusion principle? Is that what you're saying?
Well, not like the Pauli exclusion principle, but just the fact that x times y does not equal y times x.
They don't commute.
Yeah, they don't commute.
So in other words, the reason
have a common basis.
The reason we don't see them all in the diagonal form is because then they would commute, and then it wouldn't be physical, because that would imply that you could measure x, y, and z.
And moreover, they wouldn't represent 3D rotations, because 3D rotations don't commute.
Ah, right. Well, that's another way of looking at it. Yes, and three-dimensional rotations do not commute. Yeah, two-dimensional do, but not three-dimensional. Is that right? Yeah.
So already we can see out of this geometry, like we started with just the geometry of like the real plane, and we were worrying about that and interpreting it as a complex space. And now we've moved to like two-dimensional complex vectors, and there's all this interpretation involving the sphere. And we can see that there's an intimate relationship between that and statistics and probability. In fact, this is like the entire reason that we use the two-dimensional complex vector space, because in that representation, we can interpret the XYZ coordinates precisely as statistical expectation values. where this is like the probability of some occurrence, and the eigenvalue represents the weight of that occurrence. To continue with this like geometrical we could just consider any 2 points on the sphere that are antipodal to each other and make a Hermitian matrix with eigenvalues 1, -1, where those are the eigenvectors. We just do the same thing as before. Suppose you have a point on the sphere representing your state. Project that point perpendicularly onto the axis formed by those antipodal points. Then the probabilities are just given very simply. You can think about it as where here psi and v1 with the arrow above it are just the 3-dimensional vectors corresponding to those states. 1 plus the inner product between them over 2, or alternatively 1 plus a cosine of theta, where theta is the angle between them. So, you know, one kind of intuitive way of thinking about this, it's not necessarily physical, but it's like you have a sphere and you have some special axis, and then you have another point. You project that point onto that axis, okay? And now imagine that that line that you projected onto is like a rubber band, and it snaps at random in some location. And when it does that, its ends are dragged to those 2 antipodal points. What's the probability that the point that was projected gets dragged over here or over there? If you think about it, the probability is given just by the amplitude squared, or the inner product between that complex vector and the one antipodal point squared.
Is that Penrose's book?
Yeah,
Which book?
yeah.
Recognizes drawings.
Yeah, they're very distinctive. He's always put like little dots everywhere.
Yeah, his shading is. Yeah.
So, you can interpret the probabilities like literally in terms of the 3 dimensions here. And here's a little proof that like the expectation value with x, for example, gives you the x coordinate. You see, if this is the expression for the amplitude squared, or the probability of psi in the v1 direction, which say is like x plus, multiplied by 1, right? Expectation value, that's the eigenvalue. Then you got the other eigenvalue, -1, multiplied by this probability. You work it out, and since v1 and v-1 are antipodal points, this just ends up all canceling out, and it just gives you the real 3-dimensional vector corresponding to psi, inner product with v1. And that's the direction. And so this shows you that expectation values with the Pauli matrices give you just the XYZ coordinates. This part's cool, but I'm gonna skip it in the interest of time. Another interesting fact is like in terms of matrices, the Pauli matrices are orthogonal. The inner product that's relevant here is the trace of B dag times A. And when you take any of the 2 Pauli matrices, the inner product is 0. Just like, they represent X, Y, and Z axes, so it sort of makes sense that they're orthogonal. Okay, the Pauli matrices don't themselves represent rotations. They represent the generators of rotations. So like we know about the exponential function as classic infinite series that we talked about before. Well, why not try plugging a matrix into it? What does that do? So for example, e to the xt implements a boost in the x direction on a spinner. What if you, I have a little note here about how to do that, but I'll skip that actually. What if we stick an I in the expression? Before, when we had e to the I theta, we were able to parameterize two-dimensional rotations. If we stick an I into the matrix exponential and use our Pauli's, we can get three-dimensional rotations. So that e to the negative I x theta over 2 implements a 3D rotation around the x-axis by an angle theta. And the factor of a half has to do with the fact that SU2 is the double cover of SO3, and we're not going to talk about that right now. So these rotation matrices are unitary matrices. In other words, like rotations should, they preserve the norms of vectors, the lengths. And it's a fact that if you exponentiate a Hermitian matrix, like the Pauli matrices are, you get a unitary matrix. And so you can think about a Hermitian matrix as being a kind of perhaps multi-dimensional pole. And the unitaries are kind of like rotations around that pole. Now that's a geometrical picture, but we can interpret it in a statistical sense as well. Just as rotations preserve the length of the vector, we can interpret that in terms of preserving the fact that probabilities sum to 1. And e to the IHT is the general form of time evolution in quantum mechanics. A little typo there. You have, given an initial state, you can get the time evolving state as e to the IHT on that state. This is just another way of writing the Schrodinger equation in disguise. So these rotation matrices form a representation of the group SU2, which is an infinite continuous symmetry group. For each element in this group, there's a corresponding matrix. And this is how representation theory works. We find a certain group of interest to be a subgroup of some matrix group. And better yet, if that representation is unitary, because that means you can do quantum mechanics and everything can be interpreted in terms of probability amplitudes and probabilities, even if there's still this geometrical interpretation. The Pauli matrices are generators for SU2. You can think about SU2 as being itself a kind of manifold or space. And the generators kind of tell you how to go in different directions in that space. General elements of SU2 can be written as just a linear combination of Pauli's with, some I's stuck in there. And if we put rotations and boosts together, we get SL2C, the Lorentz group in disguise, and they are nothing other than the Mobius transformations from before. And here's the connection. Here's our Mobius transformation, AZ plus B over CZ plus D. Well, we can represent that as a 2x2 complex matrix with unit determinant, where we just take A, B, C, D and stick them in a matrix. And it's what we were doing already. So, feel free, instead of using the Mobius transformation as, that acts on a complex number, you can use this matrix to act on a spinner.
Sometimes
what does SL2C stand for literally?
Special
Lorentz? Is it special Lorentz?
It's special linear group.
Special linear.
Yeah. And that just has to do with the fact that the determinant is 1.
Special.
That's what the special is.
And the two in the C refer to what now?
It's two-dimensional.
Two-dimensional.
Two-dimensional and
Complex.
Oh, complex. Okay.
Given that Pauli talked about a hidden rotation, given that spin includes the notion of a dimensionless spin quantum number, given that that the very idea of spin is an abstraction perhaps as far from the underlying reality of things as what we find in the Schrodinger equation. And given that you like to do animations, 3D animations, show me right now a 3D animation of how you conceive spin.
Okay, I mean, I'll skip ahead if you really want,
But Victor, spin is not in physical space.
Oh, it is.
I just said
That's what I'm saying.
dimensionless.
No,
I
it-
just said dimensionless. So I'm trying to conceive of it geometrically, in
But
spite of the fact that it's dimensionless.
But Matt, it's an internal space. It's not in three-dimensional physical space.
No,
It's in internal space.
It's definitely in real 3D space. It's not internal.
Well, yeah, I mean the X, Y, and Z spin, but
The rotations.
when you talk about the rotation, when you talk about spin itself in one dimension, that's an internal space. It's not.
No, it can be literally interpreted as describing the magnetic field, like the pole of a little quantum magnet. It has real physical significance in terms of the like real 3D geometry. It's different from the other internal groups.
I'm thinking of isospin.
Yeah,
Isospin is an
Spin-
internal space.
Spin is not in an internal symmetry.
Yeah. Isospin is in an internal space. Yeah.
That's exactly right. So I'll explain how we get to this thing in a second. I'm sorry this has taken so long. Maybe I should have led with the animations, but they're in there. Don't worry. Yeah, I did it.
Okay, so explain what I am looking at the present moment.
Yeah, so like this is a spin 3/2 particle evolving under some random Hamiltonian. The arrow in the middle gives the expected value of the spin axis, the axis it's rotating around. The yellow arrow at the top is just for fun. That represents the complex phase of the overall state vector. And the points on the sphere, we're going to talk about how to interpret them physically, but it's analogous to the case of like a qubit where there would just be like one of these points, but for a spin J particle, you can have 2 J points. In this case, it's spin 3/2, and so there's 3. And kind of like one way of thinking about them is as vortices on the surface of this sphere.
Given that you're using the sphere, right, as the sort of underlying geometry, given that the first visualization of the supposed visualization using electrons to image photons does not resemble the sphere in any way. It's sort of mildly parabolic, a slightly flat-ended parabola with a tiny ridge on it. It's like it does not resemble the sphere in any way. This is our first visualization of the wave particle duality. So then, so this is just a convenient way to visualize.
Can we talk about what this is first? I don't believe I was part of that.
So, this picture is interesting that I'm showing you right now. It's not of a quantum spin. It is an attempt at visualizing a quantum spin, but like not of a single electron, but of like a pretty much like relatively small magnet.
But is this like some artist's impression, or
No.
So then what is it literally?
Post this paper. I can't explain their fancy way of imaging things.
Okay.
But what I want to emphasize here is like this provides a good intuition for like basically what we're talking about. It's like this is of a dipole, so this would be a spin 1/2.
Is this like a still image, or is this accumulation of a lot of like measurements all shown together?
I don't even know. But
This is the picture you have on your meetup
Yeah,
site.
This is my screensaver.
Yeah. Oh, right.
so you see that like it's like a tiny little magnet, and it has like a north pole and a south pole, and like the magnetic field's like going crazy around it. Like this is like a flattened image of it. And you see that there's these like holes, these like little vortices at the North and the South Pole. Like those are these, so that in the spin J case, it's like basically we're saying like these points are like where those little holes are. I should say though that it's like, you see there's one hole, like a North Pole and a South Pole one. So these would be like, say like all the different quote unquote like North Pole ones. We'll come back to like how to think about this as sort of like multipolar representation of spin.
Is that like a bar magnet or a current loop?
It's
The previous.
yeah, well, it's kind of like both. It's in some sense, it's so these represent like the magnetic flux lines.
It looks more like a current loop. The flux lines for a current loop.
Like picture this, it's like a 3D thing that's been like flattened to the plane to like visualize it, you know, so like North and South here, like imagine them as, you know, the North and South pole of the sphere. So we're basically, you know, you can think about that there's these like magnetic vortices like on the surface of this like sphere, and like
well, this brings up an interesting question that brings us right back to the very first presentation about the notion of the atom as the indivisible. As soon as you move into the realm of fields, you get into quantum field theory where you dispense with particles and you just have oscillations in a field is what we refer to as a particle, as a convenient way of describing the nature that we can't really quite image, or didn't do so at least until recently. So what is the significance beyond you know, the equivalent of you know, having iron filings so as to visualize the magnetic lines of force? What is the significance of the roundness of that is sort of that the pole is organized around? Does it bear any relation to your conception of what a particle is, or what?
Yeah, to answer that question, I'm gonna defer because we won't be able to have time to go through it today, but one of the things we're gonna do in the future is show how you can view quantum spin as like kind of the simplest example of a quantum field theory itself. There's another way of thinking about spin in terms of two harmonic oscillators that keep track of up quanta and down quanta. And, you know, it's basically your second quantizing a spin half particle. And so you can even view these little spins as themselves being kind of like simple examples of a kind of quantum field theory.
If there is any,
I'll come back to that. I can't.
This is another question that, you know, could, you know, needs to be opened up. But if there's any reality to our notion of spin, right? And if, you know, every fermion somehow maintains this spin 1/2 condition, even if you move from, you know, up to down, from, you know, clockwise to counterclockwise, then how, if there's any genuine underlying reality to this, how is it possible to shift direction and still end up in this process with the same spin number? This to me is utterly paradoxical, utterly inexplicable.
Victor, spin is quantized.
You're
That's
like,
why it's got to be half integer.
Like why a spin half particle always stays.
But it just strikes me, if you're going through a physical process of moving from up to down, from clockwise to counterclockwise, however you want to conceive of it, that there's going to be some alteration to this system. How does it possibly maintain? You're saying it's quantized, that you're using the definition and the description. That doesn't help us. How does it possibly maintain, you know, half integer spin if it shifts from up to down or clockwise to counterclockwise? I think this is like,
right. Well, so
You're saying why doesn't it go through the middle or something like that? That kind of
why doesn't it pass through a series of phases?
Well, my impression is that this is like spin is kind of like the most quantum mechanical thing. You know, it has like absolutely no classical analog, and And
Also,
I don't know.
also, it's a non-local phenomenon. It happens instantaneously.
Yeah.
I mean, like measurements aside, you know, there's nothing mysterious about like the transition from like a spin pointing up to like a spin pointing down. You know, I mean, you just rotate it. And the thing is like, because we're working with a complex vector space, any point on the sphere can be represented as a linear combination of two antipodal points on the sphere, right? Like that's the significance, like what I'm saying before, that like, if I have two antipodal points on the sphere, they're complex orthogonal. And so they form a basis. And so I can expand any point on the sphere in terms of like any axis. And so, you know, there's nothing strange about something being in a superposition of both up and down, because that just corresponds to like a point on the sphere, like yet another point.
But Matt, I think Victor wants to know why it doesn't go through a continuous
phase process, some
change.
kind of transition.
Yeah, because it's non-local. It happens instantaneously. It's like entanglement.
You're talking about are you talking about measurement or just rotating a spin?
I think he's talking about measurement.
Either way, it doesn't matter.
Like actually experiencing the thing somewhere in between up and down. Like in real life, no?
Victor's trying to equate it to a macroscopic magnet. A macroscopic magnet, yes, has to go through a phase, a transition, a continuous transition, but spin is a non-local phenomenon. It's like entanglement. In fact, spin is entanglement. You know, if you have two particles that are entangled, you measure the spin of one, the spin of the other one is automatically determined instantaneously. There's no transition period.
Oh, okay.
I've been thinking about the entanglement issue. It's one of the things that Matt started with, but it strikes me that it's kind of a lesser version. I'm wondering if there's not some boson like the Higgs, in the sense that Higgs is not a force carrier, that is somehow harmonizing the various quantum numbers of the particles that are entangled, so that it's actually some other bosonic process that would explain the very existence of entanglement, because it can't simply happen, and it's not simultaneous. It's not violating special relativity.
You're looking, Victor. You're looking for hidden variables. That's what
Oh well, there's nothing but hidden variables. We'll get into that.
But John Bell proved that Einstein's local hidden variables cannot exist.
Okay, that's not what I mean when I talk about hidden variables.
No.
That's a complex argument. Let's leave that aside.
Yeah. Okay. Yeah. Like, let's not talk about entanglement too much right now.
But this is it's the same thing. It's a non-local phenomenon.
There's two things that are happening that might be confusing. Like, one is how to interpret a superposition of spin states. And the other thing is, what the heck happens when we measure a spin? All right, two separate questions in a way, but related. Now, I submit to you that from what I've told you, a superposition of spin states should not be mysterious in the least, because a superposition of spin states is just the spin pointing in a certain direction. In other words, I can fix 2 points on the sphere that are antipodal and describe any point on the sphere as a linear combination of those two orthogonal complex vectors. So in this situation, there's absolutely nothing mysterious about superposition. It's
also described. It's also described as clockwise, counterclockwise. There you talk about the alteration of a physical system, and it would require some. In the physical realm, would require some change to occur, some transition to occur.
Clockwise, counterclockwise things for polarization, not for spin.
Can I say something? I gave a presentation at the New York meetup on Bohmian mechanics. There are two interpretations of quantum mechanics. There's the Copenhagen that we all know and love, that we were taught, and there's Bohmian, which is a non-probabilistic, non-local interpretation.
Yeah. So what I'm proposing here is something kind of in the middle. It's
But
neither of those
what
two
Bohm
specific.
says, just to answer Victor, what Bohm says is that superposition doesn't really exist. That when you apply a magnetic field, you're forcing it into spin positive or spin negative.
Look, it's
And it's a non-local phenomenon. It happens instantaneously.
Think about it like this. At the time that quantum mechanics arose, one popular philosophy of science was called positivism. And positivism was like, when you're studying a phenomenon, treat it as a black box. Some things go in, some things go out. And you want to interpret the probabilities of outcomes given preparations. Now, the quantum spin, like say a spin half particle, can be described like in a geometrical way as something spinning around an axis. But when we use unitary representations of it, we can describe the direction it's pointing in as a complex superposition over outcomes.
But that's
There's
Copenhagen.
a geometrical thing that also has a statistical interpretation.
But that's only the Copenhagen interpretation.
Well, in any
Bohm's-
interpretation, because it's,
No. Bohm says that you have to make the measurement before the spin is determined.
even, no matter what your interpretation is, like the definition of an expectation value is a bunch of like winnings times probabilities. And however you want to interpret it, that's the form that, you know, this thing has. And so whether you regard it as really being probabilistic or statistical or whatever, it has the form of an expectation value.
Is there a very quick summary of what the Bohmian kind of would be? I wish I knew at this moment, like
well,
what his basic
that's
principle.
Moshe, you know, last week there was some very interesting.
Well, I actually gave the presentation the week
Yeah,
before.
I'm sorry, I missed that earlier. Yeah.
Yeah, well, a lot of people missed it. But essentially, Bohm does away with all these probabilities. There's no such thing as probability. There's something called the quantum potential, which again is a non-local phenomenon. And this is an answer to Einstein's hidden variables, except Einstein was looking for local hidden variables. This is non-local.
So what's the, my impression is that, a term that normally you ignore in like Hamilton-Jacobi formalism of classical dynamics, you keep and you say that's the quantum part.
No.
But there must be something that is easily invoked that you sort of to say Bohm is not the final answer. So what is the argument that usually comes up with this?
When you said Hamilton-Jacobi,
Yeah.
Bohm describes quantum mechanics using the Hamilton-Jacobi equation, and in addition to the external potential, there's something that is called the quantum potential, which comes out if you derive the same you start with the same Schrodinger equation, but you manipulate it mathematically in a different way, and you find, oops, a hidden variable. But this hidden variable is not a local hidden variable, it is a non-local hidden variable, which means that changes are instantaneous. And relating this to spin, Bohm does away with all this superposition stuff, and
So isn't it sort of like all the mysterious stuff gets moved into the quantum potential, and so it's like you have classical particles moving around in some quantum potential and all the waviness is to do with the quantum potential and its dynamics, and you see it, the consequences of it in the motion of the particle.
What Bohm does is you can actually predict particle trajectories, which is something that, using this quantum potential, which is something that Copenhagen can't do.
Well, like, can I, break in for a second here and say, in the case of, skipping ahead past the part where we go into like how you can get this representation of spin with all the points, I can reformulate the Schrodinger equation for spin as this, where this is the change in time of one of those roots, one of those points on the sphere. And what this is like kind of a classical theory where there are interactions, forces that each of those particles on the surface of the sphere feel that depend on just the current location of the position, the relative location of that point with the other points taken individually, the relative location of that point with the other points taken two at a time. In other words, you can completely describe the quantum, the Schrodinger, like unitary quantum dynamics of a spin particle evolving under some Hamiltonian as a completely classical system involving these n-body interactions between particles on the sphere. Does that mean, however, that the thing really is that classical system? And I would say that maybe, but it's not at all clear. And I think Bohm mechanics is something similar, because it's not that weird that a classical system could be encoding all the same information as a quantum system. For example, my computer does it all the time. My computer is a purely classical system that when it does my quantum calculations is encoding all the same things that a quantum system is encoding. So it's not at all surprising that there are often classical models of quantum systems. But whether that implies something about the ontology or the way the world actually is not at all like a natural implication of that.
Your computer is doing a mathematical analysis, but what actually happens in the real physical
What I'm
world?
saying is, like, what if the Bohmian picture is just like that? Like, you've essentially built a kind of classical computer.
Yeah, the Bohmian picture is very analogous to classical physics, but certain things are non-local phenomena, and they occur instantaneously, unlike classical physics, which, you know, nothing can happen faster than the speed of light. Things don't happen instantaneously.
Sure.
But in Bohmian physics, and even in Copenhagen, you have non-local phenomena, like changing spin, like entanglement,
Yeah, I mean,
and the quantum potential that Bohm comes up with.
Spin can change. I mean, before it seemed like there was a question about whether the J value of a spin can change. Like, can a spin half turn into a spin one or something like that? And like that can happen too. Like when
particle decays, yeah,
and stuff. Like they can change their, you know, total angular momentum value.
Well, the particle is changing. It's a different particle. But a fermion cannot have a spin one. It can only have half integer multiples.
Right. Yes, that's what that means. Yeah. Okay, so you guys want to hear a little bit
There's
about...
an instance where the helium atom can have spin 0 and act as if it's a boson.
Yeah. But,
But
that's not an elementary particle. That's a composite particle. So things are different for composite particles.
Who's living in the neighborhood with a crisis?
What's that?
Is that the
corner from fire?
Aren't we all living in a neighborhood with a crisis?
Well, we're quieter about it by us.
Isn't it called Earth?
People ask me all the time if I'm under attack by terrorists. There's a
What do you tell them?
firehouse around the corner from me.
That's you.
Crisis every 10 minutes.
Right. So Matt, I didn't want to deflect away from that very interesting result you were showing there.
Yeah. Okay. Yeah. Let's get. I'm sorry.
With the,
I started this.
No, it was a good point. You know, I've been talking for like a very long time, and I did not have nearly enough visualization scattered. So I'm glad that we put that deeper.
So tie some of what you've said in the broadest sense to the to the end point, to the visualization.
Yeah. So here's how it works. Ultimately, those points on the sphere are going to be the roots of a polynomial. We're going to be representing a quantum spin like on the space of polynomials. We can just consider, say, a monomial. Like there's just a power, just z to the 1. we can think about that as analogous to our like two-dimensional complex projective vector. In other words, if we had like some complex number alpha, which we upgraded into a little vector 1 alpha, we can form a polynomial z minus alpha that has the root alpha. So it seems like we can represent, you know, these things like literally as polynomials. But we have a little problem. Like, what if we had that, like alpha was infinity, or the vector 0, 1? Interpret it as a monomial that like doesn't have any roots because all the powers of z are gone and there's just the constant term. And so you're like, oh, what do we do? And the answer is to interpret that polynomial as having a root at infinity. And that works in the higher dimensional case. It's like if we fix our dimension of the vector space to be, say, 4, we have all these polynomials, z to the third, z squared, da, 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 da. But what if a and b, the coefficients, were both 0? We're going to add 2 roots at infinity in order to keep track of those missing terms. So there's a rule. If we lose a degree, we add a root at infinity. Another way of thinking about that is in terms of homogenized, a homogenized form. In other words, we work with a 2-variable polynomial. In other words, instead of having C1z plus C0, we have C1z plus C0w. And so you see, if we have this function f of wz, we want it to have a root at 1, 0, then we should pick the polynomial just z. That has a root when z is 0 and w can be anything. Similarly, w0 has a root 0, 1, and so on. If we want f of wz to have root 2, 3, then we should choose the polynomial 2z minus 3w, and that'll have the correct root. So, you know, there's like a little minus sign you got to keep track of. So then we can use this construction to generalize the representation from spin half to spin j, where we use the roots and interpret them as 2j points on the sphere. And this is kind of amazing because we're taking a normalized spin j state, which there's a typo here, which lives in 2j plus 1 complex dimensions, which is 4j plus 2 real dimensions, and we're representing it as a point on a 4j plus 1 sphere, but that's also a constellation of 2j points on the 2 sphere. Crazy. Okay, but moving on. Suppose we had a, let's actually see it, a degree 2 polynomial. Let's have one that has 2 roots at 2, 3. So we just have 2z minus 3w squared, and we get this little guy. If we want a polynomial with 2 roots at 1, 0, it's just z squared. 2 roots at 0, 1, w squared, and so on. So we have this correspondence here. These form like a basis, these little polynomials, z squared, zw, and w squared. It's got these homogeneous roots, and it's got these inhomogeneous roots here. So if you're freaking out about the infinity thing, just homogenize, and then you're good. Now, what's amazing is that, but makes sense when you think about it. If you have a 2-star constellation, it can be written as a complex superposition of those 3 constellations. Like you have, the constellation z squared, which is 2 points at, say, the North Pole. The constellation w squared, which is 2 points at the South Pole. And zw, which is a point at the North Pole, point in the South Pole. Any 2-star constellation can be written as a linear combination of those 3 constellations. If you have generally a spin j state written as a ket like this, you can convert it into a polynomial using this little formula, which keeps into track the negative sign and a little normalization thing. This is like the Majorana polynomial. If you do this, then the roots will come out right. And where does the binomial coefficient come in? It relates to Vietta's formulas. I'm gonna go quickly. Okay, so we can check it out. So this is a visualization of, say, the eigenstates of x, y, z for just a spin half.
You're beginning to spin at the rate of a quantum particle here.
Just try to go quickly. in the case of spin 1, I won't go through it. You know, there'd be, actually, I'll just go through it. Let's do spin like 3 halves. So you see, say for Y, it's one where there's 3 points at the North Pole, 2 points at the North Pole, 1 at the South Pole, 1 at the North Pole, 2 at the South Pole, 3 at the South Pole. Any 3-starred constellation can be written as a superposition of those 4 constellations. And in fact, you can do the same thing for, you know, the X eigenstates and the Y and the Z eigenstates. All right, I'm gonna skip that part. And so, okay, this is a fun visualization. Here we see a spin 3 halves particle evolving under some random Hamiltonian. And on the side, you see the different Z eigenstates. And the yellow arrows represent just the coefficient. So like this is just, you know, the standard basis for spin is just to use the Z eigenstates. And so these yellow arrows are just the coefficients of the polynomial, basically. The coefficients of the vector in the JM representation specifically. And so at each moment, you can see that this constellation of points on the sphere, which is completely definite, can also be described as a complex superposition of these 4 constellations. And then let's go back to this, the one we were doing before. Because there's a couple interesting things worth pointing out about it. Sorry, one second. So, all right, just want to get my little controls right here. So I'm going to pause it. I'm going to clear. How do I do that? Sorry. Clear the trails. Okay, so like one thing I've set it up here is like I can press keys on my keyboard and like apply the X, Y, and Z operators in the appropriate dimension. We'll come back how to calculate those. But you see, they just rotate the star rigidly. So it's like it really, really works. You know what I'm saying? Like you get the equivalent of Pauli X, Y, Z in the appropriate dimension, and when you act on the vector, it just rotates the roots rigidly, like in a 3D rotation. If the thing's evolving under some random Hamiltonian, we could measure the energy. Ping. Oh wait, that's a boring one. Let's do that. So crucially, in an energy eigenstate, the constellation remains fixed. What happens if we perturb it a little bit out of that energy eigenstate? Like I'm just gonna rotate it a little bit. You can see that the points begin precessing around their former locations. And this is the famous Thomas precession. If we keep perturbing it, you can see that, yeah, they still kind of going around those points, but now
you're going to create Milankovitch cycles if you keep up.
Yeah. Oh yeah, it reminds me, I should turn on the little thing, yeah, that keeps track of the trails. So, you know, the more we perturb it out of an energy eigenstate, the more the roots start, you know, permuting among themselves and so forth.
Just right here, is there, because I'm not yet used to thinking of this representation with ease. So these points are, can I physically interpret them at any frozen moment? Like,
yeah.
These things? I know there are roots in this representation, but like someone handed that to me and I've got a Stern-Gerlach apparatus. Like, what do I expect based on that sphere image? You know?
Bring back the Italian so that Andre and I can start reading it aloud.
Oh yeah. So yeah, I should go back to that. Yeah, where was it? So this is from Majorana's original paper from 1932. And this is for like a spin half particle in a magnetic field. This zeta I here is the root, And he's found the time derivative of the root, like I was saying before, in terms of hx, hy, and hz, which are just that's the vector of the magnetic field.
And here he's trying to solve the general like case of a spin J system.
Yeah, so like I'm just kind of skipping around here, I guess, but like.
Or like, but in that paper, his
Yeah.
like what the title was.
Oh yes, that's exactly right. Yeah, on something, on a spin, yeah, particle, and yeah, I forget exactly the title. It's in Italian anyway. It's funny because I don't know, like I don't know that much Italian, but it's nice to be able to like look at math papers because you can kind of follow it along, even if you know.
Right. Yeah, there are so many Russian textbooks. Like that you can just basically read it.
So here's like we're definitely not going to get to this full story today. We'll pick up, this stuff next time. But we can define the so-called spin coherent states. And you can think about them as all the constellations that are like where all the stars are at the same point. Okay? And then you can show that, this representation of a spin state as a polynomial is just in some sense taking the vector and evaluating the inner product at the spin coherent state. In fact, all the spin coherent states. Sorry, that didn't make any sense. Sorry, there's a couple more things I have to say.
It was an incoherent presentation of the spin coherent states.
Yeah, I know, right? Okay. The spin coherent state is a state where all the stars are at one point. So now imagine evaluating the inner product with a spin coherent state that's precisely opposite to one of the Majorana points that we've been talking about. The spin coherent state is the probability basically for all the stars to be in the same location. But we know there's a star in the opposite direction. Therefore, that probability has to be 0. So here's the operational meaning for those individual points. They represent the directions along which there is a 0% probability that the spin will be entirely in the opposite direction.
And is there a reason why you just don't have them pointing in that direction, and then you can just say that direction?
Yeah.
The interpretation comes second.
Part of the drama comes when we'll go into this. Like in terms of representing it as a polynomial, or the polynomial that represents all the stars flipped antipodally. And it relates to the fact that there's like always like a north and a south pole and stuff like that, even if there's multiple poles. So like you can interpret the Majorana points like specifically as, well, if I look at the probability that all the stars are in the opposite direction, then naturally that's just 0. And so the Majorana points are opposite to the zeros of this like probability amplitude function, which is like basically a wave function on the sphere. Alternatively, you could just flip everything antipodally and whatever, but that's...
To go from the sphere to a physical, like if I'm in the lab, I still have to like reverse map that to like Euclidean space or something. Or can I just sort of see all the arrows pointing that way? If I aim my Stern-Gerlach system that way, I'm going to get no,
so
I will not get entirely spin in that direction.
Orient the spin-Gerlach apparatus opposite to a Majorana star, then you're never going to get the state where all the stars are up. In other words, all the stars are like up in that direction. In other words, like
the maximum, like the highest level of J
state. In other words, you have, for
J state.
J, negative M to M, you're never going to get like the highest M state in that direction.
Okay. And it's that's real space. That's sphere.
Yeah, it's just the real.
Like, hey, it's pointing like to my right. To my right. I'll move them in that direction, and I'll move the Stern Garlock that way. Okay.
Yeah, really. It's crazy.
Yeah, that's pretty.
So, yeah. So, well, since it's already pretty late, what would be more interesting to hear about right now? Like, I can go in a bit more into how to describe the dynamics of the spin in terms of the roots. I could talk a little bit more about measurement, or a little bit more about, well, let's leave it at that. Those two choices.
Maybe
I think
we could spend time on asking questions.
I personally am burnt out, so I don't know if I can take any more new stuff from you.
Yeah, this will be good. We got sort of laid the groundwork, and we'll get into some of these interesting derivations next time. But yeah, please, any questions?
Give me a physical explanation, intuition of a constellation. What do you mean by a constellation?
So the way that I kind of think about it is that, imagine you have a tornado. It's like on the earth or whatever. And there's this one tornado. Like that tornado is, dragging the wind around it. And like arguably that's like imparting like a kind of angular momentum to the atmosphere, you know what I'm saying? You could also think about like a bar magnet has like a north pole and a south pole, and like the field lines go around it, and that picks out like an axis, and it's oriented, because it's like north pole and south pole. So in the former case, you could imagine a world where there's like multiple tornadoes, each swirling the atmosphere around it. And that would impart to the atmosphere kind of like fancy kind of angular momentum. Similarly, for a magnetic little particle, you could have not just a dipole, but a tripole, a quadrupole. And you'd have like multiple kind of axes. And the magnetic field is, be kind of some funky thing. So like in the case of spin, literally, like you can sort of picture it as these like vortices, the eyes of the storm, arranged in 3D space.
I think if you don't mind,
What does the velocity of the air correspond to?
What is the what?
The velocity of the air in the tornado. Velocity.
Well, I'll say that, when you act with the Pauli matrices on different representations of spin, different J values, they like rotate faster or slower depending on the J value. So I would say that it relates to whether it's a spin half, spin one, or spin 3 halves, I guess.
I was going to ask, it's not clear to me for whose benefit this representation, serves. Like, to be thinking about it, is this like for the mathematician, like Maharana? I mean, maybe was that like a calculation innovation? Because
so originally it was a sort of innovative way of calculating. It ended up being easier to just describe, like get the little equation that governs how the roots evolve in time. Because like think about what I'm doing in my simulation, right? Like I choose a random vector, and then I choose like a random unitary matrix basically for the time evolution. And then like I evolve it like each time step. And each time step, I convert this vector into a polynomial, and I find the roots, and I project them to the sphere, and we look at it. And then I do it again, and again, and again, and again, and again. And so I can only do that because I have a computer, right? in each instant of time, I have to solve for the roots of a polynomial. And so I need a fast computer essentially to be able to do that. You know, in Majorana's day, it's 1932, you can't do that. So what he was interested in doing is finding the equations that govern the roots themselves and then just solving for their time evolution, which is easier.
As you do it more and more often over time, do you come closer to a simulation of what you conceive of as the underlying system, or is it still a random process?
So, you know, I keep emphasizing that when it comes to this interpretation of spin, or this way of looking at spin, you know, superposition is not that mysterious, in just the sense that, you know, I can take two polynomials that each have a set of roots or a constellation, I can add them up, and then I get another constellation. So that, you know, since a constellation can be broken down into various ways in terms of basis constellations, it's not that the geometrical meaning of a complex superposition in this case is very transparent. In terms of measurement, you know, the situation is interesting because it's like, you know, I go into the whole thing here, right? So it's like, you know, when you send a spin half particle through the Stern-Gerlach apparatus, it splits into 2 beams. Send a spin 1, it splits into 3 beams. And note, like, that's the dimension of the complex vector space that we're using to represent it. So it's like, you know, you can represent a spin state like as some points on a sphere. Great. But like, why use complex vectors? Like if it really just points on a sphere or whatever, I mean, why bother with the complex vector? And the point is that, well, the dimensionality of that complex vector space is the dimensionality of the number of outcomes to that experiment. And the components of that vector can be interpreted as, you know, the probability amplitudes that give you the probabilities of those outcomes. So the thing is like, in itself, I can take a spin and it's like, what basis is it in, right? I could expand it in terms of Z eigenstates or Y eigenstates or any set of whatever number of orthogonal constellations. And that doesn't matter to the spin in itself. Like, it doesn't care. It's just the difference between describing an XY point, you know, in this basis or this basis or this basis. Like, basis transformations are not real. Like, they're just perspectives. The thing is, though, you know, measurement distinguishes. Like, measurement, think of it like a filtering operation. And, you know, only one thing can happen. And all of a sudden, this decomposition into basis states, which formerly was arbitrary, just a matter of mere mathematical description, now becomes relevant. Because the experimental situation that you've set up distinguishes between the different basis states. It treats, you know, up in this direction differently than the way it treats down.
You pick a set of basis states. You don't have the freedom to.
By the experiment that you set up.
Yeah, you don't choose one basis state. You decide the set, like the orientation of the reference frame. Yeah.
Very much so, yeah.
So
that,
because it seems a lot of this visualization is for like a way to visualize what's happening in calculation, because ultimately we're always interested in the physical picture, you know, and we know that in between measurements, you have an evolving complex thing, the wave function or spinner or whatever, and you can't know what it's doing without measuring it. So you talk about it, the evolution is mathematical, but always in the back of your mind, you're thinking like,
yeah, but like,
it's a physical picture I'm trying to get at, right?
Like if I measure a spin and it's in the, you know, X plus direction. Okay. You know, I can just regard that as a little guy with a point at the X plus point. suppose I send it through a Stern Gerlach that measures in the Z direction. It's going to give me up in the Z direction or down the Z direction 50% of the time. And so I worry like, oh, poor me, like what's happening? How can this thing be simultaneously in some magical superposition between up and down? Like how can something be simultaneously in this outcome and that outcome? It seems totally crazy. Except it's not crazy at all. You've just expressed the point x plus a complex linear superposition of z plus and z minus. And I can expand any point on the sphere in terms of any two antipodal points.
Except, Matt.
Yeah, the crazy thing is that that's how it works. I mean, that is,
Yeah, no,
like, it working that way
that the
is what's
geometry
weird.
can also be
The
interpreted
rules are easy.
as statistics.
Except Matt, in the real world, see, we describe things mathematically because that's the only way we know how to describe them. But in the real world, at least according to Bohm, the measurement, you're forcing the particle into one direction or another. And of course, it either has to align with the magnetic field or counter-align. There's no other choice. If it were a macroscopic magnet, it would have to align one way or the other. Where it aligns depends on the direction of the magnetic field. But the point is, it's not probabilistic. It's, according to Bohm, it's the field is forcing it, or actually, ultimately, the quantum field is forcing it into one direction or another. This thing about superposition is the Copenhagen interpretation, and not everyone accepts that anymore.
Well, but it's not really the Copenhagen interpretation. Like, do you know what I mean? Like, I'm just saying that, like in any interpretation.
Yeah.
I think Conway said, like, this is just what happens.
Yeah, it's like if you have a spin that you've measured to be in, say, like the x direction, x plus direction, and then you measure the spin in the z direction, it's like you can really think about the reason that you get 50-50 is because, you know, when you project this vector onto that vector, it cuts it in the middle.
Let's stay in your mathematical realm. You know, what is the distinction between the description of spin, geometrically or otherwise, if what we call a particle is really a probability cloud, what we call a particle is really a 3D wave packet, or what we call a particle is just an oscillation in a quantum field? How does, Michael's making the point about our representational systems in science that are mathematical, how would it distinguish between those three descriptions: probability cloud, three-dimensional wave packet, and oscillation in a quantum field?
Look, if you had macroscopic magnets that are aligned randomly, and then you apply a magnetic field, half of them are going to align with the field, and half are probably going to align in the opposite direction. Now, X, Y, and Z, or any other direction, of course, the particle is going to align, whether it's an elementary or a macroscopic particle. A magnetic particle is going to align in the direction of the field, or opposite. Those are the only two choices. And the probability is going to be 50-50.
Yeah, but classically, there's a time it takes to flip, and you can witness the thing in between the two, opposite ends. But
and certainly
in the quantum picture, you can't see an intermediate state.
No, because there is no intermediate, because this is a non-local. Classical physics is local. And this is what bugged the hell out of Einstein. He wanted quantum physics to be local, but there are phenomena that just are not local, entanglement being the most famous.
I don't remember who said it, but I remember someone mentioning this notion of like the conservation of weirdness. That it's like you can pick your framework to think of it in terms of, and there'll always be some part of that that's going to be like super weird and have no intuitive, no comfortable. You want to move it into the
weird to us because we're macroscopic beings, and we're accustomed to seeing things as local phenomena. All macroscopic phenomena appear to be local. But not all phenomena on a microscopic level are local. Some are non-local.
Well, I'm not challenging that, but yeah. But I'm saying it's perfectly reasonable to feel that that's weird in like a special way.
I mean,
yes,
we are in the quantum
That's
realm.
how our brains evolve.
Stars are in the quantum realm. The cosmos is in the quantum realm. So the distinction we make between the classical realm and the quantum realm is not so clear. It's especially not so clear when you think that they've taken a buckyball, which is 60 carbon atoms, and send it through the double slit. And now they've taken, as I told you in one of the previous sessions, they've taken a macromolecule of around 2,000 atoms with 25,000 times the mass of a hydrogen atom and moved it through the double slit.
Okay, look.
So, how does the distinction
Victor,
between the classical realm and the quantum realm hold up when you start talking about that?
Victor, if you study Bohmian mechanics, if you had come to my presentation at the New York, you study Bohmian quantum mechanics, he explains this. A particle does not go through two slits simultaneously. What happens is that you have a quantum potential, a real physical potential, but a non-local potential that guides a particle through one slit or another.
I mean, I just think, like, in terms of this Bohmian stuff, is that, like, it's very interesting and it's very important in such a mathematical description as possible. But I feel like it's like an attempt to hold on to a world which, like, ignores the lessons of relativity. Like, it's like an attempt to hold on to this picture of the world as like, oh, it's a bunch of things like happening in space.
But Matt,
I want to mention something that I think would fit right into this moment that maybe is interesting and useful. That there was relatively recently there was a measurement that showing that
points about Bohmian mechanics.
Can I just add this one extra thing about what is going?
Mechanics?
Am I on mute?
Electron, for instance.
There's two people talking at the same time.
The electron exists as a particle. The particle never goes through two slits. It can only go to one slit. But the particle is inseparable from its guiding wave. With each particle, you have one and one only guiding wave. The guiding wave is specific to this particle. It is not the guiding wave for any other particle. And this guiding wave is basically a solution to Schrödinger's equation.
But Bohm rejected the whole idea later of the guiding wave.
Both slits. The guiding wave in a spin experiment is both up and down. It is not up or down. It is up and down. The guiding
I just want to mention this result that happened that I think might challenge some of the claims here.
So the particle now, as far as the uncertainty that we observe for an electron that follows a perfectly deterministic path, that in order to know where the electron is and which path it is taken, we must know the initial conditions. The initial conditions are not clearly known because the initial position of the electron is given by the probability amplitude, which is simply the square of the wave function. The same as in Copenhagen, basically the Born rule, you take the psi star psi. This gives you the probability density for finding the electron at a given point. And depending on at which point it is, this will determine which trajectory it will take. But since you don't know with certainty what is the initial point, there's no way you can know with certainty which trajectory it takes. So the upshot is that the prediction of Bohmian mechanics are identical to the prediction of Copenhagen mechanics. No difference whatsoever. But you have a completely different interpretation of what it is that's happening. In Copenhagen, the electron keeps switching between being a particle and being a wave. Sometimes it acts as a particle, sometimes it acts as a wave. And this was enough to to drive someone like Wheeler into destruction to the point where he said that until you measure it, it does not exist. There's no existence except during measurements, because he couldn't make sense out of it. Is it a particle or is it a wave? Bohm explains it. It is both a particle and a wave. The two are inextricably related. It is not sometimes a particle, sometimes a wave. It is both at every point in time.
I think it's a wave that exhibits particle-like behavior.
Essentially,
I think it's always a particle whose properties are wave-like.
All right, here's
here's
the thing. If you study Bohm, I agree with everything Moshe said.
Basic concept.
I agree with everything Moshe said, and I've studied this too. But what Bohmian mechanics does, it actually gives you actual trajectories for actual particles. And we know that the particles go through one hole or another.
Well, that's the thing I wanted to challenge with
and
this
the
experimental
double
result
slit.
that came out recently.
Well, let me explain this. Because you can slow down the experiment. You can shoot electrons or even photons through the double slit, and you could see where the individual particle lands. It lands at a point. So it hasn't gone through both slits over many particles.
That last part was
Never observed it.
It's
If you
not a
don't
question
even-
of knowing where it lands. What you see is the intersection of the negative interference and the positive interference.
No, that's
And that
But
is
it's
the
not the
approximation of where the
Victor,
particle lands.
Victor, it is not the
The
particles that are
interference is an
interfering.
interference of the guiding wave.
Right.
The
It's
guiding wave
interference of the
interferes
quantum
with
potential.
itself. The guiding wave goes through both slits. It interferes with itself, and it guides the electron, the particle, to the position where you end up observing it.
You know, the crucial situation that we're in that explains like all the mystery is, you know, not entanglement or superposition, but just like the fact that this is a class of phenomena for which measuring it changes it. So that, like, even if you want to say something like, oh, it's Bohmian mechanics and this particle is following this definite trajectory, you will never see that trajectory. Like, you will always reconstruct that trajectory after the fact and tell a story about how this is like a possible thing that could have happened.
No, Matt.
You always have to erase relevant information
Matt,
to make a
in a
measurement.
similar way with the spin case.
Matt, the
Like,
physical world.
I can describe the spin evolving in its glorious superposition as just a classical system of particles experiencing, you know, forces. And from that, like, I too, just like in Bohm mechanics, can deduce all of the probabilities for all the experiments, and each of those points will take a completely definite trajectory on the sphere. But, you know, at the end of the day, our process of measurement, even if you just want to regard it as because we're macroscopic beings, is such that we change the answer by asking the question, period. Like, we have no access to the state until we measure it, and then we've changed it. And so we can only do repeated experiments and reconstruct in retrospect, so that, like, we can come up with like models of how the world is, but they can't be ever directly confirmed by just looking and seeing if it really does take that trajectory, because it's always a story about the past that we're telling.
And Matt, this is the problem. Classically, when you make a measurement, the measuring device has a negligible effect on the system because you're using a small device to measure a large macroscopic system. You have just the opposite in a quantum measurement. We're using a huge macroscopic device to measure an elementary particle, so of course it's going to change the system. But the point is this. The point is this regarding determinism. And Bohm is deterministic, unlike Copenhagen. The point is, if I can get my brain in gear again, is that physical processes go on regardless, the universe exists regardless of our consciousness.
Sure.
You know,
You
nature does.
I support that.
What humility! What humility!
Yeah, I'm a very humble person, and you want to get right down to it. And a measurement is just another interaction. And when you're doing a measurement with a macroscopic device, Of course it's going to change the system, but Bohm can actually calculate the actual trajectories of particles. And like Moshe said, it is the quantum potential that goes through both slits. The
Then
quantum
you can ask, what is the
potential-
quantum potential? Why can I not
Okay.
observe a quantum potential
Well,
without a particle?
XYZ, I don't know your name, but you mentioned it
I'm Michael.
before.
I didn't
Michael,
mean it to come out like that.
he's your
Just like me.
counterpart. He's your
That was
avatar.
that's some default setting from Zoom. I didn't
You
mean that.
mentioned it before, Michael. You brought up Hamilton-Jacobi.
Yes.
When you put the Schrodinger equation in the Hamilton-Jacobi form, you have an extra potential that Copenhagen never discovers. You have an extra potential, which we call Q. It's the quantum potential. And that is what guides the elementary particle. And that actually shows you the actual trajectories of these particles, something Copenhagen can never do for you. And there's nothing
Right.
probabilistic.
But normally when we talk about potentials,
it's
they're physical things that we know what we're.
It's completely deterministic. There's no more probabilities involved. And
Okay, Michaels, can I try to cut through this? Look,
Yeah.
what you have is you have probability and you have equations of motion. And the equations of motion in quantum mechanics are non-local. And the only then question becomes, where is the probability? Is the probability happen at the measurement or at the original state, or as other theories of quantum mechanics have during the path? So that's the question. Where is the probability?
The only probability is the fact that
the only probability in Bohm is at the beginning. What is the initial state? And the only probability in Copenhagen is at the end. When does the measurement happen? And the only probability in these GRW kind of things are in the middle when there are continuous collapses or repeated collapses. But they all then derive equations of motion to get the same result. And all those equations of motion have to depend on the non-local, and this is to you, the old Michael, they have to depend on the positions of the other particles. That's where Q comes from. Q is derived from the positions of all the other particles in the universe.
And it's
so
changing.
Everything in the end depends on the particle positions in the universe and gets mediated for this one particle in its collection and called Q. But it isn't that there's some special field out there in the world. They're all just derived from the other particle's position.
And it depends, you're right, on all the particles in the universe, or if you can get an isolated subsystem on all the particles in that isolated subsystem. But the point is, and this is what makes it different from classical physics, is that Q, the quantum potential, changes instantaneously. You don't have that occurring in classical physics. But also, as Andre said, the probability...
Prove it, kiddo. Prove it.
The probability...
No,
because
Michael, you are wrong. You do have it in classical physics.
Victor,
Most certainly.
It gives
in
you
classical physics, in Newtonian mechanics, the action is instantaneous.
I'm curious to know what Michael was going to say.
If the sun disappears, the Earth will.
But no one's going to defend Newtonian physics as the final story.
It gives you a Bohm gives you a physical picture of what's taking place. It doesn't say, like Niels Bohr said, well, forget about the physical picture. Forget about your intuition. We can never know that. Bohm says, no, Niels Bohr was wrong. Bohm gives you a physical picture of the trajectories. And let me just say what Andre was alluding to about the probability coming in at the beginning. The emission of elementary particles is a stochastic process, whether it goes one way, whether it's emitted one way or the other way. And that is what determines which particular trajectory an individual particle will take. It depends on the initial conditions, which is probably a Gaussian distribution or something close to it. Well, every distribution approaches a
There are
Gaussian
no
distribution.
stochastic processes in nature. We use probability to describe not only the quantum realm, we use it to describe Brownian motion. We use it to describe an the climate system,
Well,
an
but I
n-body
believe that in
problem
all
in
cases other than
space,
the quantum system, we're using
I
it as an
agree.
approximation.
or a
Victor,
cosmological
I agree
process.
with you. Victor, I agree with you. But the thing is,
I don't.
it's stochastic only in the sense that there's no way for us to determine it. But once, once
I
the
agree there.
particle is,
I agree there.
once
It's
the particle,
deterministic, but it's indeterminable.
once the particle is emitted, its trajectory is completely deterministic. That's what Bohm says, and he can show it. Copenhagen says just the opposite. Everything is probabilistic.
Can I butt in there? Because, I mean, to really do justice to like Niels Bohr's position, it's like, he's not saying that, oh, you just kind of have to like ignore whatever the particle's doing between measurements. What he's saying is that our classical pictures of things correspond to metaphors. And phenomena in the quantum realm are mixed metaphors. In other words, like for every classical picture, there corresponds to like an experiment. So that like position, you know, the classical metaphor at the end of the day bottoms out in like, in real space, you could like distinguish between like it's here, or it's here. Like the concept of like a wave, you know, in the classical physics is like a certain way of distinguishing between this interference pattern, et cetera, et cetera. And, you know, his claim is that like there may be multiple metaphors that are appropriate to describe a given quantum system. And the use of one metaphor might exclude the other one. And that bottoms out in like this experimental situation excludes that experimental situation. If you measure the position, you change the momentum. If you measure the momentum, you change the position. And therefore, you know, you can't just keep the two classical pictures in your head simultaneously because, you know. But
No, but what Copenhagen says, Matt, I have to disagree with you. What Copenhagen says is that quantum physics is a black box. We don't know what's going on inside. That's not good enough for a lot of physicists. That was not good enough for Bohm. Bohm gives you a physical picture of what's taking place.
And well, but I'm saying that Niels Bohr said that actually the problem isn't that there's no physical picture, but that there's multiple points of view. I mean, that's why it inspired Cubism. That's why all the artists start like describing things simultaneously from like multiple angles at once.
So why is Bohm's interpretation not taught in school? They only teach this black box style quantum mechanics. And by the way, and that's a political
I can answer that.
A political decision.
I would say that like in the end, quantum mechanics isn't a theory of physics. To quote Scott Aronson, it's the operating system that our theories of physics.
No, that's math.
In other words, what is physics about?
Nature doesn't know about operators. Nature doesn't know about math.
I know. I'm just saying about us.
I'm exhausted. I'm going to leave.
Math is a construction.
Circuit overload here.
Math is a construction that we invented in our brains. Nature doesn't know about math. Nature works on rules.
Yeah,
and we use math to try to approximate what nature is doing.
Let's take something very basic into account
when we talk. Easiest math, basically, for studying the world. It's like you use complex vector spaces, you use matrices to represent the symmetry groups. No matter
and in every case,
you're working with,
it's an approximation.
In
every case, it's an approximation.
Let's think for a moment about one of the key origin points in quantum mechanics, which is the Schrödinger equation. He actually writes it in 1925. It gets published in 1926. So this is occurring. This is an abstract description of an essentially unknown or utterly unknown quantum system. We have there's the electron in 1897. There's the nucleus in 1912.
Victor,
there's the neutron in 1920. We still haven't found the existence of the proton. We know nothing about quarks. We know nothing about neutrinos. We know nothing about the Standard Model, the particle zoo, any of the other particles that might be there. We know nothing about a theory of absolutely everything, or a theory of everything, or a gut theory. We know nothing when the Schrodinger equation comes into existence. So it is an abstract description of a system that we have altered through the act of measurement. And so what we're talking about when we talk about quantum mechanics is mathematical models, and it's utterly incomplete in its view of the nature of things. It's something that gives us a whole series of accurate, reasonably accurate outcomes. We're able to start to develop quantum computing and quantum cryptography, and even the LIGO system depends upon quantum mechanics, but it is a completely incomplete view of things.
Can I say
Quantum
something?
In its current form, it's so powerfully predictive that
Quantum field theory expands on it, Victor. Quantum mechanics, even under Copenhagen interpretation, is not the be-all and end-all. It doesn't explain particle creation.
Wait, can I just say something?
Yeah, sure.
So, when you first learn about partial differential equations, you learn about wave equations, right? And solutions to wave equations form vector spaces. And we think about those solutions as each describing, a way that a string or something is vibrating, okay? The Schrodinger equation, it's, you don't even have to think about it as taking place in like position or like whatever, as like that being the variable. It's just the matrix exponential with a little I in it.
And the idea what in it? A little what in it?
A little
square root of -1.
Yes, it's just the matrix exponential where it's just e to the I. I couldn't hear what you're saying. Your operator. Okay, and so what is the point? The point is that the vectors are now to be interpreted as like probability amplitude vectors. And the idea that they're vectors or have a finite length is as much to say probability sums to 1. And so the thing describes what? What is the thing it's describing? It's describing how probabilities flow.
No, that's only in Copenhagen, man.
No, oh,
it's
whatever.
only in Copenhagen. Let me tell you what those vectors are. Those vectors are not in physical space.
Look, we talked about metrics, right? Like at the very beginning, I was like, oh, you have two Minkowski vectors, or just t, x, y, z vectors you stick in the little Lorentz metric, right? You can think about the observables in quantum mechanics as providing a metric or a measure on probabilities. So that if you look at the expectation value, psi h psi, it's a sum of, the probabilities weighted by the eigenvalues. And so you can think about that, like the thing that underlies all the different modalities, angular momentum, position, energy, all all
Matt, can I ask you a question?
Concept is probability.
Matt, do you actually believe that the universe is probabilistic and not deterministic?
Well, I'll say two things.
Some of us believe that the universe is deterministic. Nature knows exactly what it's going to do. Because Copenhagen can't explain it, doesn't make it probabilistic. It's only probabilistic in Copenhagen, not in Bohm. Bohm
Michael
gets rid of those probabilities.
Michael, listen. This keeps coming back to your question of why is Bohm not taught in school? The answer is that Bohm is not a progressive research project. That Copenhagen ended up inspiring quantum field theory.
It's political, Andre.
Listen to what I'm saying.
Just let him finish. Let him finish, Michael.
Listen to what I'm saying, Michael.
Yeah.
Is that Bohm could not inspire the next step. Copenhagen inspired the next step. That's why. That's
really?
What happened.
Which next step?
That's a good explanation.
Quantum field theory is a completely different theory.
That's why.
Quantum field theory is a completely different theory. It
No, it's
relies on second quantization.
Right,
It
but it's
relies on field
inspired by.
excitations.
That's right, but it's
Excitations of
inspired by Copenhagen, not by Bohm.
quantum field theory is completely different from
I
quantum
agree it's
mechanics.
different. I agree
Quantum
it's
field
different.
theory describes a real physical field and particle creation and annihilation through excitations of that real physical field.
I agree.
Schrodinger's field is not real. It's an intermediate mathematical step
That's right.
towards a conclusion.
That's
I'm
right.
not
Space is
necessarily
not real
disagreeing with that.
space.
That's right. And that's why it was inspired by it. It's an intermediate step. But could I get back to this other question about the particle zoo? Newton proposed the universal law of gravitation before they discovered Pluto. So it's a question of what's the ontology and what are the rules that apply to any portion of that ontology. That's why you don't need to know about a lot of particles before you can start quantum mechanics.
Yeah, and to piggyback on that, it's like, if you accept Bohr's idea that, there's mutually exclusive multiple pictures on a given system, like the position picture, the momentum picture, like what's the one thing in common to all the different pictures? It's probability. At the end of the day, whether you're talking about energy or position or momentum, there's outcomes and they happen with certain probabilities. Like
Matt, that is not what Bohm says.
And
That's
so
not what Bohm. This is strictly Copenhagen.
I'm agreeing with you. I'm saying, like, why is it?
Are there probabilities in classical
forms the
physics?
mathematical machinery of quantum
Are
physics.
there probabilities in classical physics when you know all the parameters and their derivatives? No probability. Classical physics is completely deterministic, and so is quantum physics when you use Bohm's approach.
Michael, can I just ask, since you seem to be in favor of the Bohmian view of this.
Indeterminism, nature knows what it's going to do. The fact that we cannot explain it.
Okay,
is
Michael,
our
may I ask just,
Nature knows.
do you have notes from your talk that you gave that I could look at?
Well,
I didn't realize I was missing like the key moment in history of the universe.
I believe it was recorded. I think Moshe may have recorded it. Maybe not.
Okay.
I don't know.
Well, speaking for myself, I'd like to sort of better understand what you are thinking before
Google,
hear any more.
Google it. You can study it on your own. Google it.
Well, I have a feeling that I would miss something that you would find important.
It's a completely different, physically intuitive interpretation of quantum mechanics. Of course, it gives you, it's consistent with Copenhagen, as it must be, because they both give you the correct answer in the end. But there's no probabilities involved.
I mean,
Bohm is completely deterministic.
It's just like, I think like the answer that it's hard to generalize Bohmian mechanics is the right one, right? How do you extend it to handle, quantum strings? What about vibrating quantum membranes? What about
Bohmian mechanics is strictly non-relativistic. To go to a relativistic system, you got to go to quantum field theory, which is, again, quantum field theory is not a successor to quantum mechanics. Quantum field theory is a completely different theory. The field is a real field, and excitations of that field give you creation and annihilation of particles. That's something that was not known in quantum mechanics.
It's an expansion. It's not like
Michael,
totally different.
We're going to see, like I said, how we could interpret a quantum spin as a quantum field theory. It'll be interesting when we get there.
This was the fireworks we were all waiting for.
Yeah, I was saying for next time, can we get to this part earlier? Just
Yeah. It's funny. I wrote out all the spin stuff as like one essay, and then I was talking to my friend. He was like, "You should like split it up into different sections." And then I ended up like adding like a lot more material to each section. So I kind of apologize that this was as the case as it was at the beginning. I will keep the fireworks going.
Yeah, Matthew, we want to see the final written version of this at some point. After you come back and change everything you want to change.
Yeah, well, if you go to the heyredhat.github.io, you can see that the notes are up there.
Well, let's continue this next time.
Okay, can I just make a suggestion to the new Michael that if he wants to see these arguments spelled out exactly as clear as I know where they're spelled out, you should read this very short book by Tim Malden about the foundations of quantum mechanics, and it spells out all the different views and what their soft spots are.
You know,
Do you
Wikipedia.
agree with that, Michael?
Wikipedia
would give a.
Wikipedia does a credible job.
Well, I have my background as well.
I started at Wikipedia, and that will lead you, and also Scholarpedia does a credible job, and they get right to the point, and they do all the derivations too, and no, but why isn't Bohm taught? And I gotta put this in because this is important. Bohm published this paper in 1952. What was going on in American history in 1952? The McCarthy hearings. People were being accused of being communists, and so was Bohm. Bohm lost his position at Princeton University and went into self-imposed exile, and he was persona non grata for the rest of his life. The physics community didn't want to touch him. And besides, the establishment was married to Copenhagen.
No, there's a whole bunch of Soviet physics that is perfectly accepted now. So
yeah,
Bohm is welcome back in.
If only our politics were married to Copenhagen, we would be in a lot better shape.
Everything is political. And you know what's political now? And this is a danger to scientific advancement. String theory, for which there is no empirical evidence. And the string theory departments at universities, particularly Columbia University near me, is the most powerful financially and politically. And what it does, it sucks up all the oxygen and all of the financing away from legitimate physics research.
They really struggle to get funding.
String theory began to fade a number of years ago, and it seems to be in a waning phase.
Tell that at Columbia University. The only thing about string theory that ever gave it credibility is that it predicts a spin 2 particle to mediate gravity.
Yeah.
Where is this spin 2 particle? Has anybody ever found it? We don't even know if it exists. And that's the whole...
It's being expressed in gravitational waves.
Oh, no. Einstein showed gravitational waves. You don't need spin 2 particles. Einstein was not a particle physicist.
I happen to have a spin 2 particle right here, and that spin 2 particle is going to explain its existence to you.
Then you get the biggest prize that could be awarded, and you become the chairman of the string theory department at Columbia University.
I want to make just one last offer of a reference, and then I'll get going. For those who are less excited about these sensational points, like myself, I like the history a lot. And just I don't know if you've seen this on YouTube. There's lectures by Dirac at Florida State University.
Yeah, totally.
Which I really liked. I watched them a bunch of times. It's like really soothing. His voice is like so calming. Anyway, but the first of those 4 lectures, he describes, at least from his point of view, the story of quantum mechanics. So, from the horse's mouth, so to speak.
Sean Carroll has a YouTube presentation on the history of quantum mechanics.
But Dirac is like, you know.
Sean Carroll doesn't know what he's talking about. A lot of what he talks about is just plain wrong. We can get into that another time.
I mean, I
really recommend it just for those who like to see the.
You really can't separate out the politics. Like, I mean, what you bring up.
You can't separate the politics from anything.
Like, I'm pro Bohm. I mean, I just think that the Bohmian interpretation just needs to be seen alongside the context of there's many different models, classical-ish models of quantum systems.
Matt, do you know?
A lot that we can learn from.
Let him finish, Michael.
Yeah.
Whether it can be generalized to handle all situations, and therefore implies that the ontology of the world really is like that, is another question. And as far as the determinism thing goes, it's I don't, when I say that I kind of believe in the probabilities, so to speak, I don't know, man. I don't know if there's some weird thing going on in the very tiny world that just leads to the appearance of the probabilities or not. But I always go back to, there's a story from the Middle Ages called Buridan's ass, Buridan's donkey, who's owned by a philosopher. And, the philosopher spends all day riding this donkey, and the donkey's getting exhausted. And finally, at the end of the day, they get home, and the donkey is both hungry and thirsty. And the philosopher sees this and decides to do an experiment. He puts a bucket of oats next to a bucket of water in front of the donkey. And the donkey's like looking at the one, looking at the other. And the thing is, the donkey is like equally hungry as he is equally thirsty. And so he's like, I gotta go, I want both, but I gotta go for one first, you know? But like, there's literally no reason for me to choose one or the other. And so the donkey just passes out.
It's predetermined.
A human would realize that if they don't pick one, you're not gonna have either. So that's
It's predetermined, and
it's hard to know
Taylor's theorem shows you that everything is predetermined. There is no free will. There's no free will for a donkey or for a human being. Everything is predetermined.
What if you? But see, that's
What's Taylor's theorem?
That's a metaphysical like belief. Like
Taylor who?
It's not Taylor's.
It's not a metaphysical belief.
It's not metaphysical.
You would have to be a
It's empirically
divine
observable.
being who is completely outside of the realm of physics, outside of the realm of nature, to make a free decision. What you have underlying consciousness is
so why? Why does it have to be outside?
biochemical processes, electrochemical processes, neurons firing. You have systems of neurons, arrays of neurons that are shifting in every instant. You don't control those processes.
All predetermined by initial
What I'm saying is,
conditions.
no, but like, what if it's literally ambiguous? Like something's
It's
going
ambiguous.
wrong, and there's two paths.
Predetermined by
No
initial
reason to
conditions.
go down one or the other path. What happens?
What happens in a physical
Predetermined
system?
by initial conditions, Matt.
In a
Yeah, right.
physical,
Someone says like, oh, it's the initial conditions. Like
Matthew,
there's no two
wait.
paths that are ever
in a physical,
exactly identical. You just follow it out a bunch of decimal places.
Matthew,
and there will
when
always
you
be
solve
some difference.
Matthew, when
Is
you
that really
solve a
necessary?
differential equation,
I think that's a very good point. That
a
Matt just
physical system, the strongest force wins. The strongest array of forces, constellation of forces wins.
it's
So
free.
in consciousness, you have this absolutely irreducible system of complexity that's at work, and constellations of forces via the firing of neurons establish what the strongest constellation will be in that instant, and that's the decision that you make. And there are some experiments that show that you've made the decision before you're even able to express it. So that's controversial, but I would say that we must follow Kant. We must act as if we were free, but in fact we are not divine beings. Therefore, we are unfree.
And nature, I repeat, nature doesn't know about probabilities and our mathematics and the shortcomings of our mathematics. Nature doesn't know about these things. Nature operates by rules and
right, but what I'm saying is like
That's-
nature
a
follows
a lot of
the
semantic
nature
subtleties
doesn't
there.
definite
nature
rule.
doesn't throw dice.
But what if there's a situation where there's exactly as many reasons to do A as to do B?
It has to do with initial conditions.
But
Now,
wait, Michael,
when
I'm
you
saying,
solve-
what
let me
if
answer
it
that.
was
When you-
literally identical?
when you say,
Like what I'm saying, like,
that's
what
what
if the initial
when you
conditions
solve
were literally
that,
identical?
when you
But
solve
Matthew, it's not literally identical. It's like the matter-antimatter situation, and matter will win out. And it's just the decision that you make is the one that you had to make, because it won out because the array of forces was greater than the array of the opposing
Can
forces.
I answer this mathematically?
So?
Matt, when you solve a differential equation, Matt, you get a general solution. The way you get your constants is by initial conditions or boundary conditions. So everything is determined by initial conditions.
I agree with that. Wait, we have a
Are
hand.
you telling me
that's
initial conditions are probabilistic? No, they come from what came before. Nature doesn't know about probability. Nature works according to rules and goes from step A to step B according to rules.
Well, I like to throw a nuttier thing in there, which is that the weirdness of quantum mechanics says that we are in a simulation and there's a bug in the program because you could have inconsistent stuff happening.
Which quantum mechanics are you talking about? And quantum
Martin
mechanics is only
Heinsdorf
an
has a
approximation.
But
smile
quantum
on
mechanics
his
is just part of
face
the gamer's
that is
design who designed our
wider
universe,
than
and there's a bug.
13.78 billion light years.
Science is based on empirical evidence.
Michael, wait, I have a question
It's
for you,
not
Michael.
based on science. This is science fiction. And
What?
so is string theory. String theory is science fiction.
Wait,
Until
Michael,
we
I
have
have a
some
quick question
empirical
for you.
evidence, it's science fiction.
Michael, I show you a picture of a diagonal line,
Yeah.
and I ask you, is it horizontal or vertical?
It's a mathematical construction.
No, I'm
There's
saying
no such
literally-
thing as a line.
No, dude, literally, what if I show you a picture of a diagonal line, and I put a gun to your head, and
Yeah.
I say, pick one, vertical or horizontal?
The one I pick will be determined by initial conditions,
Right.
plus whatever new conditions you force on me. But it's deterministic. There's
What
no
I'm saying is that-
probability.
First of all, whether it's deterministic or not, in terms of that situation, no
Yeah.
one could predict you better than chance, all things considered, because you have as many reasons.
Only
to be
because you
vertical
don't know.
as
Only
to
because
be
you don't
Matthew,
know
it's
the initial
deterministic
conditions.
but indeterminable. And so
Only
it
because
that's
you
seems
exactly
don't know the
probabilistic.
initial
And we
conditions.
need
But nature
probabilistics
does.
to foresee the outcomes, but it is determined. We
But I
simply
think that's
can't
challenged by the
determine it.
Cohen-Specker theorem, and
Well,
where you show that there's at least one example of a case that can't be fully described even in principle.
Nature determines what's going to go on by the initial conditions. You may not know what the initial conditions are, but nature certainly does.
We don't, and
Nature
we never
doesn't
will.
throw dice.
But like,
I
I'm
agree.
just saying, like, why though? I mean, like, what's the problem with imagining a world where, like, sometimes the initial conditions can be, like, literally identical, but there's two paths. There's literally no reason to choose one or the other. And so then the thing that happens is just
They
random.
can't be identical. There's
Why
no
can't
such
you
thing
be
as identical.
You're weighing it prismatically. You're weighing it perspectively. You're a complex being. The world is complex. All the inputs that went into you,
Yeah.
whether
But then what about
genetic,
the
whether
individual
upbringing,
spin?
whether the zeitgeist, they are inextricably complex. And so what seems to be in balance, either or, is not an either or. Either is going to win because either is a smidgen stronger or significantly stronger or exponentially stronger. Either is going to win
I like
over
that,
or.
but, you know, what I think is interesting is then when you consider the case of just like a single spin half particle, and you ask it, it's pointing in the x direction, and you ask it, are you up in the z direction or down in the z direction? There isn't anything that can influence the electrons.
The initial conditions,
No,
Matt.
but what if I'm saying they're the same, dude? Like, I'm literally telling
No,
you.
they're not the same. They start off
Yeah,
at random.
No,
I
like,
agree with
if
Matt,
you
they're the
measure
same.
it- If you measure it, it then ends up in
When you measure it,
and
you're forcing it into a particular position when you're measuring it.
I prepare
and-
them identically.
And
Like,
how
you know
does it
what I'm saying?
go? How does it go up or down? Depends on the slight variation of initial conditions, the
Well, what I'm
initial
saying is, like,
randomness.
what if there were no slight variations in the initial conditions? Like, can you accept that possibility?
There's no. How's that possible? They'd have to be in the same place. at the
Why
same
should I
time.
imagine
Well, then there's a source of fluctuation that sounds pretty random.
Like, why?
There's no such thing as random in nature. Believe me, nature knows what it's doing according to rules. Random is just a concept we come up with because we don't know how to figure out the exact initial
I
condition.
am shocked, Michael. You agree? I agree with you utterly on this. It's just that we have to stop thinking of indeterminacy and think in terms of indeterminability.
I
We
like
have
that,
to,
yeah.
the way a proper description of the cosmos would be, whether at the quantum level or the cosmological level or the astrophysical level, is it is hideously complex and therefore not reducible. We will never know what the initial conditions are, but nonetheless, those conditions existed and went through their transitions and, you know, altered states. And so what we have is an utterly deterministic universe that is indeterminable at
No, it's
every
not.
level, from the quantum level to the
Victor,
cosmological
it's not that it's
level.
indeterminable. It's that we are ignorant of what the initial conditions
We're
are.
not divine beings, so you're damn straight we're ignorant.
So if I may
Well,
jump in
divine
for a
beings,
second
that's
here.
a whole other,
Sure.
we don't
I've
want
been waiting to
get
hear from
that
John.
here.
Yeah, I just got to get going. This is actually the first meeting that I was able to finally attend in person,
Welcome. Yeah.
and I saw some of the YouTube videos previously. So thank you very much, Matthew, and everybody.
Well, thank you. I hope to see you again.
Yeah, see you at the next
Oh.
one.
Bye.
Take care.
Bye-bye, Jonathan.
Yeah, I like this idea of distinguishing between, literal randomness, the appearance of randomness, and
Come on, hurry up. I'm missing
appearance of
Oprah or something on
determinism.
TV.
I think that's an important distinction. And I'm not going to be an ideologue about it. Like, I don't know whether, really the world's, fundamentally indeterministic or not in the sense that we've been talking about. Although what I will say is that I don't think the experimental evidence forces you to choose one or the other. There's as many reasons to choose the one as the other.
This is a philosophical
It's a
difference.
philosophical.
It is philosophical, but all evidence points to determinism, and that's where science has always been headed, towards determinism. We only believed in magical things before we could explain things scientifically.
Well, but you could really
Science,
argue,
the
though, that
direction
you
of
believe
science
that
is towards
Is
determinism.
just magic in another form. You want to believe in a principle of sufficient reason, that everything happens for a reason, that God has
Sure do.
every little thing, and he left it to the initial conditions of the world to just like unfold.
It's not a reason. It's not a matter of a reason. It's a matter of, forces, processes that are arrayed, and they alter their state in each instance. The cosmos is unique. Nonetheless, it unfolds as it has to unfold.
Okay, I'm going to say something to
I guess I just
support
like the
Matthew.
idea that the universe is indeterministic, because it just seems more like cool.
I hope it is. Yeah, that's more
Particles are
fun.
fucking anarchists. They're like,
There's
"Fuck
Not
you,
one
like,
thing-
I don't make the
indeterministic,
rules, bitch. Like, I'll do
indeterminable.
whatever the
Just
fuck
shift-
I want.
Just
like,
shift the language.
There's
It's not a
one
matter
thing-
of indeterminacy
Well,
and
I mean,
determinism. It's a
there's
matter
one
of an
thing we can't
Unclear where the
indeterminable
evidence for that is.
universe that has an underlying order that we do not yet understand and may never understand. Do you realize that they just recently found 2015, 2016, the X17 particle, which is expressed, for instance, in the decay of a beryllium atom? It may be a fifth force. I mean, dark energy may be a fifth force. There may be a boson, as I described, which is causing the harmonization of the various, quantum properties of particles, what we call particles, which I don't even believe in their existence. So what we
They're
have
field
is,
excitations. I told you, QFT talks about field excitations.
yeah, I
which can
agree.
create
I
and
agree
destroy
with
particles.
QFT. I agree with QFT.
Yeah, and it's a real field. It's not a Schrodinger field, which does not exist in real space. It exists in Hilbert space, which is a configuration space. It's not real space. It's an intermediate mathematical step towards
They're
the
not teaching
answer.
QFT in the schools, that's for sure.
And QFT is a completely different theory from Copenhagen quantum mechanics. People say, oh, it's the next logical progression. No, it is a completely different theory. And the most precise theory that man has ever come up with.
Come back the next time armed, ready to defend yourself.
Who, me?
Because the rest of us will be armed to the teeth, Michael.
I have COVID-19. I'm going on an incubator in a couple of minutes. I'm not gonna. I can't be around to. That's why I had to get it all out now to educate you people.
No, but this is definitely the right debate to be having. It's like if
Yeah, but you know something.
battles weren't fought.
I will come to Matt's defense. There's one thing that is not.
He's a brilliant kid. He's got a great future ahead of him.
There's one thing that's not deterministic: quantum fluctuations, if they exist. Now,
How old are you, Matt? How old
How
are
do you
you, Matt?
explain that?
I am 30.
Which
You're
may
30
have brought
already?
the entire
Okay.
universe into existence.
Yeah, you're a brilliant kid, so you got a good future ahead of you. Real good future.
But stop studying Copenhagen and probabilities. That's the wrong path, believe me. And again, Bohm is not taught because he was accused of communism. And
No, I mean, that is,
you
for
know, when you're politically
Oh.
unpopular, it doesn't matter how correct you are. Hey, look, Galileo was almost burned at the stake for being scientifically correct. The only reason he wasn't is because he had connections in the church. His daughter was actually a nun who was very well connected in the church. Otherwise, Galileo would have been burned at the stake.
Bruno was burned at the stake. Bruno foresaw living beings living in other star systems throughout the cosmos.
I see that every night when I go to bed. I'm going to change my name to Bruno so I can be famous.
All right. Good night, Bruno, and everyone else. I gotta go.
Yeah, we should probably call it.
It was fun. It was a lot of fun.
So this is the shouting match that it degenerate. You know something? At the New York, I got to get it all out here because at the New York Quantum Theory, I'm on the verge of being expelled because they cannot tolerate controversy.
Is that the word for it? Is that what it's called?
When I brought up the fact that Bohm was a communist, I thought they all had a fit. We don't want to hear about politics. This is about quantum physics. But like Matt said, you can't separate politics from anything. It's in every aspect.
Or Matt or someone else, can you post to the site some sort of references?
Politics,
I could learn more about the origin of this political steering of what is being taught.
Google David Bohm and Bohmian mechanics, and you'll be steered to all the right things.
On
No,
politics,
I don't have
follow
any
the
books on
Copenhagen
his,
interpretation.
no, I don't have any books on like
Let me
the
tell you
political
something.
motivations.
David Bohm wrote an excellent quantum mechanics book that doesn't even mention his own theory, because he knew that in order to sell the book, he had to kowtow to the established Copenhagen, or else they would never have published it.
But I'm asking to know more about what you know, so maybe you don't confess it.
I have a book that's called How the Cold War Changed Physics. I'm going to go look in there and see if they discuss
Well, you know,
David Bohm.
Look, the greatest scientific progress in the 20th century, at least, is because of war or the space program.
Other subject.
Yeah, and you can see the way that
That's unfortunate. That's very unfortunate, though.
You can see the way that the Nazis, for example, they don't like this Jewish physics with its relativity and indeterminism and all this stuff.
That's the thing.
This movement in the 30s to restore a deterministic picture.
Hitler considered quantum physics, quote, Jewish physics. And that's why the smart Jews left Nazi Germany in time. But even in World War I, the Kaiser came to the top scientists and said, I want you to sign a pledge that your scientific research will only benefit the war effort. And Planck, everybody from Planck on down signed. You know who refused to sign? Einstein.
That's my boy.
And then when Planck's son was killed in battle in World War I, Planck came to Einstein and said, you know, Alfred, you were right. We should not have signed that pledge to the Kaiser. But this is what goes on. This is what goes on in every war.
Yeah.
They talk about the good war, like World War II was the good war. Was there ever a good war? War is a failure. War is a failure of diplomacy.
Absolutely.
Absolutely.
And I think one of the things, too, that's kind of interesting is, a lot of these Copenhagen people ended up building the bomb and then getting, these high profile kind of government-funded positions after the war.
Yeah,
and
so now where do we stand now? Where do we stand?
Let him say it, Michael. Michael, let him finish.
At the time, America was trying to posit itself as the bastion of freedom,
Yeah, right.
CIA is paying off abstract expressionists to make lots of crazy drip art, because we in America, we don't want any of that bullshit Soviet, social realism.
Yeah, tell BLM.
We got jazz, we got Jackson Pollock, and we got a theory of physics that says the world's indeterministic and free, as against those dialectical, materialist, deterministic, atheistical Soviets. So you can see, yeah, totally.
And
like, polarized on that.
without the Soviets, we would be living under Hitler's Nazism today. Well, not you and I, Matt, because we're the wrong ethnic background. But
No, Russia won World War II. That's the fact. We didn't.
without the
Russian
Soviet
fucking
Union, we would not have won the war against Germany. And you know why they dropped the bomb on Hiroshima and Nagasaki? It wasn't to win the war. That war was over. It was to show Stalin, we got the biggest weapon in the world, and don't you mess with us after the war. Do you know what Stalin said? I got to get myself some of those bombs.
Yeah.
And the Cold War, you know, people say Harry Truman was a near great president. Harry Truman started the Cold War. It lasted for most of my lifetime. And for what purpose? It was a complete waste. And you know why the Soviet Union fell? Not because of Ronald Reagan and Margaret Thatcher. That's bullshit. It fell because of corruption. And Gorbachev brought it down because he recognized
the Soviet economic journals already in the mid to late 1970s were writing about the fact that the planned economy was capable of creating, you know, things all the way up to reasonably advanced weapon systems, but no high-tech weaponry. It was able to create steel. It was able to create farm equipment.
But
it was
they
able
were
to create
missiles.
modern
They
buildings.
started, Victor,
But it was not able to create. It was not able to create consumer goods, and they were already. The Soviet economists were already writing about this in the second half of the 1970s.
It's another meetup.
That's really interesting.
Victor, they started as the most backward European country at the outset of World War I. The progress they made was incredible.
They were eighth in the world in industrial production in 1917. So they did not start as the most backward nation in the.
Are you kidding me?
They were eighth in the world.
European country.
Well,
they were eighth in the world in industrial production in 1917.
I'm thinking it's going to happen in Germany because Germany's the most industrialized nation, and you know Russia was not on anyone's horizon.
No, China.
That Marx was writing, you know, like
China. Now China gives both capitalism and communism a bad name. But China, at least China learns. At least China learns from other people's mistakes.
That's your best. That's your best line. That's your best line, Michael.
Well, it's the truth. Is China a communist country?
No, of course not.
No. Is it a capitalist country? Not that either. It's a monopolistic
Well, it's far
country.
closer to being a capitalist country. They decollectivized agriculture, small business, medium-sized business, and they began to move on large-scale businesses, but didn't go there.
Crony capitalism.
I'm going to quit while you guys are ahead.
But at least
good night.
good night.
I'll see you again in the future if time exists or whatever. Yeah. Bye.
Okay. Bye-bye. But at
if
least
time exists, good one.
The Chinese learn from their own mistakes, and they learn from other countries' mistakes. And they are in the process of not doing a rerun of the collapse of the Soviet Union in their case. United States,
they're going to collapse ecologically within
our country
within 10 to 20
nothing.
years.
You know why we learn nothing? We learn nothing because we are an anti-intellectual culture. We celebrate the guy who dropped out of junior high school and became a billionaire. That's what we celebrate. We don't celebrate education.
So true.
All these poor kids think, oh, they're going to drop out of high school and they're all going to become, Zuckerberg or Michael Jordan. Or this is the false American dream that has been sold. And we are an anti-intellectual country, unlike the European and Asian countries, which celebrate intellectuality and education. We celebrate the morons who got lucky or were born into the right family, like our dear leader.
Michael, yes. China's economy is going to collapse because they're losing their ecological base because of the rate of deforestation, because of the rate of overgrazing and over-tilling of the soil, soil erosion, loss of their water supply, as well as climate change.
About the United States, Victor, the reason China may collapse is because there's too many fucking people there and they don't have enough jobs for them. That's
have
the
a,
Chinese Communist Party's biggest fear, that they invited all these young men into the cities to take industrial
they have the
jobs,
one-child
and now those jobs are
policy,
gone.
so they have essentially stabilized their population into the future. It is
Not
Africa's
anymore.
population
Not
that is growing
anymore.
at the highest rate.
They don't have the one-child policy anymore. It was a very unpopular
There's
policy, and
virtually
there'll be
no
a
one.
revolution there if they ever try to institute it again.
There's
Because the
virtually
Chinese
no
believe
one.
in family.
There's virtually no one in China that goes beyond 2 children. As long as you're at 2.1 or below, you're at 0 population growth. China doesn't have a population issue; it has a resource issue, and so does the entire Earth. And that is the reason for the coming ecological collapse.
The Chinese are a nuclear power. They can threaten the West. That you supply us with raw materials that will bomb the shit out of you.
That doesn't help. Having nuclear weapons doesn't help. It harms you.
Nuclear weapons don't help.
No,
They're
they don't.
certainly helping the guy in North Korea. They certainly didn't help Gaddafi in Libya when he agreed to give them up. And that's the lesson that all these tin pot dictators have taken. That
Not wrong.
And Iran and North Korea know they got to get their hands on the big weapon. That's the only way
One thing that I
they'll
will
survive.
say about you, Michael, is no one would call you opinionated.
Nobody would call me what?
No one. No
Call me
one
what?
would dare call you opinionated.
I'm not opinionated. I told you. I'm going on a respirator in a couple of minutes, and I gotta educate you people before I pass on to the next.
Instead of having read Vladimir Nabokov's Strong Opinions, I think you wrote it.
What, Lolita? Lolita? You're talking about Lolita?
No, Strong. He wrote a book called Strong Opinions.
He also wrote Lolita. I'm not a sex pervert.
It's perhaps the single finest American novel after the war.
American? What kind of American is
he's
Nabokov?
an American.
It sounds like a Ruski to me.
He had an English-speaking governess, and the English language was in his skin.
What did Stalin do to his governess?
In his belly, it was a part of him.
Stalin probably put his governess up against the wall and shot her.
Lolita, light of my life, fire of my loins, my sin, my soul. Lolita.
By the way, whatever happened to Sue
A trip of 3
Lyon?
steps down the palate to tap at 3 on the teeth. Lolita.
Victor.
She was low, standing
Victor, whatever happened to
It's the
Sue
greatest
Lyon?
opening
Matthew
of
doesn't
any
get
novel
that.
in the
Matthew
history
never
of
heard of Sue
humankind.
Lyon.
Sorry?
Whatever happened to Sue Lyon? She played Lolita in the movie.
Oh,
She was like a one-shot deal. The Marilyn Monroe replacement. They won one movie.
Are you talking to us, Michael, like completely naked, sitting in your chair?
Oh, by the way, Moshe told me I have to put on a shirt to come to his.
oh boy.
Because he's recording it. So I asked him if I have to put on pants too. But let me ask you a personal question.
Who wears
Victor.
the pants in the Michael S. family?
Victor, let me ask you a personal question. Can I ask you a personal question?
Sure.
Are you part Jewish like the rest of us?
I'm 1/8 Jewish.
Because you pronounce Moshe's name Moshe. That is the Yiddish pronunciation.
Moshe, what am I going to tell you, Moshe?
Moshe is the Yiddish pronunciation. I've never heard a Gentile pronounce it that way. I only heard my great-grandmother pronounce it that way.
I've never heard anyone say Moshe.
Well, Moshe is the Hebrew pronunciation, but
really?
Moshe is like the Yiddish diminutive.
I'm a New Yorker. The only thing I ever heard was Moshe.
You're a New Yorker?
I may not sound like it at times because I lived in France for several years. So you
grew up in Rego Park.
It changed the way I speak because of all the French that I spoke.
No, but Moshe, only like an old time Jewish immigrant would pronounce Moshe.
Never heard Moshe ever.
Moshe is the way they say it in Hebrew. Yeah, it's Moses. You know, the guy who came down from the mountain with the tablets?
I know that guy.
Moshe.
I know that guy.
You know that guy?
we've had some, we've had some lively philosophical discussions.
And he was such a klutz, he dropped one of the tablets. Apparently there were 3 tablets, and the idiot dropped one of them. Go figure.
Yeah, well,
Go send a klutz.
after he
to
dropped
do
it on
God's
his
work.
foot, he needed another tablet.
Marty's getting a kick out of this. Finally, Marty smiles.
Are you kidding me? Marty had, when you were in the midst of saying what you were saying, Michael, again, you and Michael were debating. Martin had a smile on his face as wide as the cosmos.
I noticed.
Honestly, I was like, I couldn't believe the smile.
Because nature is funny. I think Art Linklater said that. Nature is funny. No, he said kids are funny. But yeah, there's a lot of humor buried in my serious talk. Pay attention.
I agree.
I gotta have supper. Matt, you're
Yeah, me
great.
too.
You're great. You really are a brilliant kid. You really do have a very good future ahead of you. A great future if you apply yourself. My goodness, you've done this. You've learned what you've learned on your own, and you seem to hover over it. I mean, you very seldom even have to pause or have a moment of humility. You have a superb intellect. Make use of it.
Wow.
And by the
Thank you
way,
very much.
Victor and I have a great future behind us.
Okay.
By comparison.
I love you guys. You guys.
And I
are
hope to
awesome.
meet Sue Lyon on the way down. But anyway, it's probably an old bag by now.
Okay, guys, it was a lot of fun.
Hasta la vista. Au
Okay, hasta la
revoir.
vista, baby.
Auf Wiedersehen.